Good morning, ladies and gentlemen. Good morning, everyone, and welcome to this workshop where we're going to be talking about solar fuels. And the workshop is called Hydrogen and Beyond, How Solar Fuels and Chemicals Will Decarbonize the World. Just give us 30 seconds and we will begin. So in the meanwhile, as we just wait 30 seconds for more people to join and for us to start, I would like to ask you to please use the chat, which is on the right-hand side, so that you can introduce yourself, your company, and also where you're joining from today. Make sure that you tag everyone, so that we can all see who you are, and we can all participate in the conversation. We have a lot of people with us today, a lot of old friends. I can see here in the chat and in the attendance list some friends and people that we've worked with for a very long time. So we thank you all for being here with us today. And we're discussing a very important issue. Let's just get into what we are talking about today. I think everyone knows what solar fuels are. We don't usually use this particular name, solar fuels, but basically it's when we turn electrons into either chemicals or molecules. It's a good way of putting it. And we know to decarbonize, sadly, electrons are just not enough. There are certain industries, certain niches in which we require to look into decarbonizing chemicals, decarbonizing molecules in order to make them low carbon or no carbon. So hence, this is what we're talking about here today, because fossil fuels just don't have a future in a decarbonized world. So we're looking for ways of making fuels that come from renewable energy. So in our agenda today, we have around 3.5 hours of conversation about this issue, about where are the consumers, about how the systems work, what kind of technologies do we have to decarbonize. So you're going to be learning about all of these issues. And at the beginning, we're going to have 3 talks essentially that are quite short, 10-15 minutes of each, where we're going to be talking about the role of solar fuels in decarbonization and in decarbonizing not only the economy but also industry very particularly. And then after that, we're going to have 2 panel sessions where we're going to be talking about making solar fuels competitive, and last but not least, we're going to be talking about cutting-edge R&D for solar fuels, the solar fuels of tomorrow. So without further ado, I'd like to ask the first of the speakers, Thomas Schleker, to please switch on your camera. Hello, good morning, sir. Also, if you can switch off your... Good morning, how are you?
Good, thank you. Thank you very much for the kind invitation.
We're delighted to have you here. So if you like, without further ado, you can start with your presentation. Just one note for everyone. If I can have everyone knowing that we're recording this session, the materials will be available, and that if you send any questions at all, please use the Q&A box at the bottom, okay? And we're going to try to take as many as we can in each time. So without further ado, Thomas, go right ahead. We have my colleague has the presentation for you. So just let them know when you need the slide to move forward.
Thank you. So my name is Thomas Schleker. I work as policy officer at the European Commission in DG Research and Innovation in the unit Clean Energy Transition, and working as policy officer on solar fuels. And it is my great pleasure to open this very interesting event by introducing a little bit to European research and innovation policy on solar fuels. Next slide, please. I would like to start with, of course, the overall policy framework. If we think about research and innovation, it has, of course, to deliver to here in energy to the energy union with the package Clean Energy for all Europeans, and of course now the European Green Deal with the ambition to become the first climate neutral continent by 2050. And recently with the climate law, the targets were updated to achieve a greenhouse gas reduction over 1990 levels from 55% in 2030. And you might have followed the Fit for 55 package in this respect with a lot of measures, also on the market side. And bringing basically together all the efforts to achieve this decarbonization. Now, internationally also, it became clear in the Paris Agreement that we can only reach the 1.5 degree target by actually really having innovation and innovative technologies delivered. So research innovation is very important in this context. And of course, when we talk about energy, it always influences a lot of other policies, being it digital. It's important for job growth, investment, and also in generally all economic areas. Next, please. I will not talk detailed about hydrogen, but of course, the European Union has a very specific strategy also in research and innovation on hydrogen with the Clean Hydrogen Joint Undertaking, and also bringing hydrogen in the global context. Recently, the Single Basic Act was now decided. So please look at this information on the Clean Hydrogen Joint Undertaking and what the European Union does on hydrogen. Next, please. Also internationally, there's now the mission in Mission Innovation 2.0. There is a specific mission on clean hydrogen now. What I will talk more about is what was from the first phase of Mission Innovation, the Innovation Challenge 5 on converting sunlight. And here the objective was to discover affordable ways to convert sunlight into storable solar fuels. But a lot of countries teamed up to collaborate on these efforts. Next, please. Now, in this roadmap, which was provided by Vision Innovation, I invite you really to look at this in detail. And I think it fits very well to the topics discussed today. The focus is on direct sunlight conversion technologies, which are of course defined in the context of existing electricity technologies and also biomass, which is harvesting sunlight, and the factors which are used upstream, and the possibilities for chemicals as well as fuels to deliver to. Next, please. There is a range of technologies covered, really ranging from photoelectrochemical up to thermochemical, photobiological, photocatalysis, etc. And PV and electrolysis is also covered in this roadmap as important reference technology. Next, please. Now, how this roadmap is structured, it has really at the core, there you see here the converting sunlight value chain. There are really the conversion technologies at core. However, acknowledging the importance of the upstream interface to feedstocks, carriers, and catalysts, and the downstream interface to where the solar fuels should actually contribute to. Can be energy, but also, of course, the chemical industry, consumers. All of this is acknowledging also the need that there are issues to be solved at system level. I think this is very important. And so several horizontal cross-cutting issues and the increasing importance of carbon cycle neutrality and also a circular economy, also including resources and materials. Next, please. The second study I would like to shortly introduce you was a study commissioned by the European Commission to 𝗖𝗏 about solar fuels research and invest. And this had really the task to define the solar fuel value chain and to perform a techno-economic analysis, how research and innovation can contribute there. Next, please. I really can only go shortly to that, but nevertheless, since you shared the slides, I invite people to look at that after. So what is important is here on the first to really clearly define the technological pathways which can contribute. Also, this study defines basically what are the base conditions for the specific technological routes, which are electrochemical, thermochemical, chemical, and biological paths. but a strong focus on really also defining the energy needs. If you look at this graphic on the right, it is really 3 steps. Basically, we have really the sun harvesting part and how to convert, and the importance of basically, again, the end use industries. So you need to bring all of them in synergy and align them to be successful. Important, what are the investment needed? This is an important part in the roadmap, the importance of investments and also other policy drivers and important market drivers, also like the carbon price. Next, please. Here, I put this only as a blend that you see what really this roadmap delivers new. The study, it is basically analysis of how the costs are structured for different technologies. So you see the yellow is capital, for example, for solar PV. Of course, you have high capital costs, but less maintenance. And so you see for different technologies here, there is really a different assembly of the overall costs. And I think this can be very interesting for the researchers also to look at, because these are the drivers where you need to work when you want to bring the cost down. Next, please. And this graph, actually, the dotted line is the increase of the fossil price, which is basically modeled on a high, let's say, very long time frame until the end of the century. And you see here 2 green-blue lines, and basically the lower one is with a higher research scenario. So basically, we see if you invest a lot in research and innovation, you can bring the cost faster down, and then you can get basically here in this example a decade earlier to cost competitiveness. So this is only one example, but a lot of this in the study. So next, please. Yeah, indeed. What you see here, this is for the overall global energy market, basically what is modeled the contribution for solar fuels in yellow. It might look disappointing if you look at it at first glance, but if we think that this is around 5% or more of the global energy demand, this is huge quantities of energy, and this means also a huge importance and potential for solar fuels. Next slide, please. Now, very quickly, I think I'm close to run out of time, but very quickly about Horizon Europe, the current EU Research Innovation Program. Next slide, please. If you think about solar fuels, of course, it is in pillar 2, where you have climate, energy, and mobility. However, please look also at other very interesting options like the European Innovation Council. Then, of course, there's the pillar 1 with all, let's say, the bottom-up research, which is applicable to this as well. And you also have basically other actions in pillar 2. So please really look at what is available in the fundings and tender portal. Next, please. Only very quickly, there are 2 topics in this work program currently, which might be of interest to you. One on efficient and circular artificial photosynthesis. This is a development, so lower TL project. Next, please. And one on direct renewable energy integration into process energy demands of the chemical industry, where you've seen the text that artificial photosynthesis is mentioned and direct solar thermochemical conversion as one of the possibilities. Next, please. Thank you very much for your attention. And I hope I could give you a short overview that there's a lot of material you can look at to also see how research innovation, what the policies are at the European level. Thank you.
Thank you very much, Thomas, for giving such a comprehensive introduction, and your keynote about what is happening and what you guys are doing, to make sure that the right R&D pathways are followed in the solar fuels and solar chemicals. So thank you very much for being here with us today and for your presentation. I'd like to now move on to the next speaker, if I may. I'd like to ask Marcelino to please switch on your camera. This is someone that you will know quite well because he's been around also for a long time. So Marcelino, just take the mute off. How are you doing? Good morning. Welcome.
Good morning. Okay. Hello,
there's a lot of friends here that we have in the audience. So Marcelino is actually going to be talking today to us and giving us a little bit more information about the Solar Fuels Now initiative. So we'll go right ahead, Marcelino.
Yeah, okay, yes, okay. Belén, can you give me the permission to share the screen?
Oh dear, hang on. You should have it already, but apparently not. Thing is with the... Okay, try now.
Okay, let me see. Yes, okay.
You should be able to because Valeria was doing it. There we go.
Now.
With that enlarged.
Hey, hello, can you see
We
my
can
screen?
see it perfectly and we can hear you, so go right ahead.
Okay, hello. Okay, my name is Marcelino Sánchez. I'm the director of the Department of Solar Energy Technology and Storage at CENER, that is the Spanish National Renewable Energy Center. Okay, I'm also the coordinator of this initiative, Solar Fuels Now. I'm going to be very quick. I'm going to make a very short presentation about this initiative. I'm going to use only 4 slides. In the first slide, I will talk about our ambition, but the second slide is what we do, what we're trying to do. The third slide is who we are now, and the fourth slide is what we expect from you. So, Solar Fuels Now is a dynamic open innovation community for shortening time to market of solar fuels and chemicals. As you know, at this moment, clean energy transition is becoming urgent. This is important. On the other side, as Thomas was explaining, solar fuels and chemicals are enablers to help this transition to happen. So we have many different technologies, different technical paths, different TRLs that need to be developed. And all these give us, is a challenge for us, but it's also an opportunity for growth, for having a leadership, not only technical and industrial, but also societal and environmental. And this is what we try to do. We try to connect this opportunity to the growth and the knowledge to the final goal. Okay? How are we going to do this? First of all, we believe that we need to act now to meet future goals. The other important things, we are having an unbounded problem-solving approach. We are also focused on IP trading and business, so we want to use this opportunity to create jobs in Europe and worldwide. And also we want to go beyond this Solar Fuels Now community to reach really the society at large, because we need to solve the problems of the society. And finally, and very important, we want to have always live information at any time, at any moment, showing what is the status of each of the technologies in the following years. Okay, our main concern is our goal is to avoid the valley of death of innovation. In one side, we have always the research, usually driven by the public sector with universities, research centers, and in the other side, we have the private sector with the commercial applications, the investors and the venture capital, but in many cases, the knowledge falls in this valley of death of innovation, and we want to be this bridge connecting the two sides. Okay, so our initiative, Solar Fuels Now, will act as a bridge to connect this research with the final application and the growth. Okay, in the end, this is the main goal. How are we going to do this? We will set up a large-scale R&D initiative with a dynamic innovation ecosystem through rigorous inclusive engagement of all stakeholders. This is not easy, so we need to involve everybody in to shorten time to market. This is important, and we want to achieve an actual impact of solar fuels in the energy transition. Okay. who we are. Okay, at this moment we are about 28 partners. Within these partners, it's just an example. We have technical leaders, we have a 𝗦𝗫 coordinator, we have also enablers as ATA and others. Final users, we have amplifiers. They are associations of the industrial associations. Also, we have companies. And also we have other partners that are acting as national contact points and also international contact points. In addition to this, we have an external advisory board made of people from the technical side and also people from the industry. And also we got so far 94 support letters with different profiles. Okay. And what we expect from you, okay? The truth is that we need you. Okay. The involvement of every player is essential for this initiative to work efficiently and to really to convert this opportunity in business and in leadership. So we want all of you, not only the speakers, attendees, organizers, etc., to be committed with our goals and share your knowledge, expertise, ideas, ambitions, concerns, your view in the field. And we need you to be the soul and the heart of this initiative. We, as Solar Fuels now, we are just a catalyst to enable these open innovation activities. And we really appreciate you being actively involved in this first event that we are doing now. Okay, I want to thank you for coming, and I want you to enjoy this event, and please be active. Let us know your thoughts and try to bring added value to this initiative. Thank you very much. Okay.
Thank you very much. Thank you very much, Marcelino. So now you've heard, why we're here today and, what are the things that we need to discuss. I mean, it is incredibly important for us to focus on solar fuels in order to decarbonize. It is the best for everyone, that we take this seriously and that we go from electrons to molecules and chemicals. So it's about getting everyone together, all the players, so that we can make sure that, we can achieve this goal as fast as possible, as cost efficiently as possible, etc. Hence, every single person's contribution is going to go a long way, to make sure that we're in the right place. And it's a matter of the whole industry to come together. So if you want to get involved, get in touch with us. There is a way, there's something, of course, that you are going to be able to do. So next speaker, Rafael, that you can see already on screen, he's going to be talking about the key role of solar fuels and chemicals in decarbonizing industry, which is by far the hardest thing to decarbonize. So thank you very much, Rafael, and welcome. I'd just like to, Valeria, if you take that off and you allow Rafael to show his presentation, so we can get ready. And keep sending. I still, there is one question for Thomas. Keep sending them. We'll try and do now 5 minutes just for Rafael, Marcelino, and Thomas to answer any questions you guys send, and then we'll move on to the next session. So go right ahead, Rafael, with your presentation.
Thank you, Belén, for the introduction, and thank you everyone for joining. Since I'm a bit delayed, I'll jump right into it. So my name is Rafael Guédez, and I am a senior researcher at the Energy Department at KTH. Like Belén said, I'll be talking or building upon what Thomas and Marcelino said about the initiative we have and why we're here today, and try to move towards the context of Sweden in particular, since this is where we are based. In that context, since maybe to some of you don't know us, so KTH is a university. It's the largest and oldest technical university in Sweden. It's very old, from 1827, roughly 14,000 students, 4,000 employees, and top 30 in engineering sciences in the world. The division I work is the division of heat and power. And what you see here is just a picture of how our campus looks like in a very atypical day, summer. And I lead research in renewable energies, energy storage, power to X, thermal systems in general. This one is more realistic of how it actually looks today, where I am based today. Now, Thomas and Marcelino already gave a lot of context to why we're here today, so I don't need to explain too much here, but I thought since we address the general audience, in its simplest definition, what we're talking about when we talk about solar fuels, it's a synthetic chemical fuel produced from solar energy. And then when I say why, when I'm asked why are we looking into this, so Thomas explained very clearly we need we need to decarbonize, and now we have a very good momentum, not only because solar energy is the one to look at because the amount of energy that we have from the sun is enormous, but also when looking into the technologies that we have today already to use or to harvest solar energy, these are cost competitive. regardless if it's solar photovoltaics, constraining solar, or just direct sunlight use. Among the most investigated fuels, we have hydrogen, syngas, ammonia, and methanol. I will come to that. But how do we get to fuels? Also, Thomas already mentioned, there are different routes. And what you see here is from left, basically, how do we get from the sun to actual solar fuel on the right? And what I show here is that there are different feedstocks needed. So including here CO2. So CO2 will play an important role there, depending on the process we have, as well as water, of course, which we're more familiar with for electrolysis. And then we have processes that after we, let's say, either we use these feedstocks by thermolysis, thermochemical cycles, electrolysis, or direct use of sunlight, we get syngas or CO and hydrogen, which are already useful as fuels, but we can further process them through other fuels, hydrogenation of CO2, etc., to finally get into fuels that can be used in the conventional processes as we use them today, such as gasoline or kerosene. So this is, let's say, what I want to highlight from this slide is not to show that there are different processes involved here at different maturity, and that the processes require then that we work towards getting them towards cost competitiveness. Now, the other background there I wanted to highlight is that if I keep on hydrogen, which is the one focus on the media mainly, today hydrogen comes mainly and pretty much almost 99% from fossil fuels. And the uses that we see on the right are mainly for refining and ammonia. So should we, maybe the key message here is that should we move to a hydrogen-based economy, we need to, first of all, not only look into decarbonizing the production of hydrogen, which I already mentioned, but also expanding the demand and making sure we have more uses for hydrogen in the industry. At KTH, we have done different studies, and compiling different studies, we see different projections. And here, what you see on this slide is just on the top, it's how demand is expected to grow for hydrogen use, driven by many aspects. So in yellow, you see how it's multiplying by, on the further left, it's actually today, sort of. In the middle, it's 2030, and then 2050 on the right. And then the graph just shows the cost depending on the technology or how hydrogen is produced, where brown and gray are all taxed for how if it comes from fossil fuels, blue when it's combined with CCS, and green typical electrolysis mainly, actually, most of the studies refer to. The bubble size are referring to the share of demand and share of production, basically. So most of the hydrogen today, almost 90%, is brown or gray, or only roughly 10 blue, and very less than 1% green. And we're moving towards, if you look at the different scenarios, towards a society where we're going to increase the demand of hydrogen drastically, and we expect green hydrogen to be cost competitive with the other hydrogen options and be the leading contender in terms of share in the market. However, having said that, if you look at this, still see that fossil hydrogen will still be cheapest unless we change our policies or are more aggressive. The demand will increase, as you see, and that will be mainly driven by green hydrogen cost reduction, but also for policies that needs to be happening to drive the existing demand and new infrastructure. So we're seeing this green hydrogen momentum, and already mentioned what it entails, but 4 key cornerstones of why we're seeing it, besides the need for decarbonization being one of them. So countries are setting legally binding targets for zero emissions. We see it very likely in Europe. We see a reduction of costs in solar LCOE, so PV or CSP regardless, as well as in technologies for using this electricity like electrolysis. We see also a broad collection of proponents compared to before. So they are now emerged from academia, interest from industry, interest from states, etc., that actually mention that hydrogen is a key vector for decarbonization. And this view is increasing among all the different sectors. Now, this has many challenges, like I already briefly touched upon. So first and foremost, today, hydrogen is still entirely supplied almost from natural gas and coal. Besides the low temperature, let's say electrolysis, most of the other processes are yet immature, and we're going to need them, as I'm going to come forth. Producing green hydrogen is still costly, even from electrolysis, though, and it also requires vast resources. So we're talking electricity, water, land, etc. So all of that needs to be addressed from a technical point of view. Furthermore, once we have hydrogen produced, or green hydrogen, it is difficult to store and transfer. So we need a lot of focus on technology development in how to manage this. And here is an opportunity actually for solar fuels, or solar fuels can serve as a storage carrier, besides being a final product itself. the development of hydrogen infrastructure today is also slow, and it might be one of the reasons why we're holding back adoption, even though some industries are interested in adopting it. And in order for hydrogen then to be more used widely, then we need to move from the typical use from oil refining and ammonia, and actually that needs to be driven by policy to drive demand and infrastructure. Now, this is what I want to talk mainly then. It's how can we use hydrogen in industry? And I particularly focus in the case of Sweden, and this is our experience and our background here. So in industry, particularly in Sweden, we have a good example of how hydrogen can be used in the iron and steel sector as an energy source and as feedstock. So what you see here in the middle is basically what I'm talking about. And typically the process of hydrogen or steel manufacturing will require natural gas or coal and use these red arrows and a blast furnace. Now the hydrogen path, however, basically replaces the reduction in blast furnace by new direct reduction using hydrogen and new technologies and electric arc furnace. So these technologies are being developed in a way to basically decarbonize completely how iron and steel is made. Similarly, in chemical production, well, already hydrogen is well established, as I said, for refinery and ammonia. And today, what we see, however, is that hydrogen can also be further exploited for ammonia, but also for methanol and other products that derive from methanol. In other industries like cement, aluminum, and glass, hydrogen adoption is also possible, but they require high-grade heat. And the one challenge we see is that these type of industries have invested already in their furnaces and processes, and changing to hydrogen require big investment. This is an example of, or a key example of a project in Sweden. So the 𝗕𝗵𝗴 project, it's targets fossil-free steel before 2030, actually by 2026. It has recently been in the news because it received the Innovation Fund award. And what you see on the right is the same I just mentioned. So the typical process of iron or steel making on the left using a furnace, and then the 𝗕𝗵𝗴 process where basically hydrogen from electricity or from, let's say, electrolysis combined with hydrogen storage, it's used for new processes in way of direct reduction and here in exposed iron for electric arc furnace. Now, hydrogen, besides potential use in industry, has an important role in transportation, and that's where you see mainly, or one of the key focuses. And even within transportation, this slide might sound a bit complex now that I look at it, but I want to focus your attention on the different, path forward. So one is clearly on converting, through Haber-Bosch processes and with the use of nitrogen to convert it into ammonia and to help decarbonize the shipping industry. So that plays a very important role. The second one, I think, relies more on the actual, heavy duty and long haul transportation. So we're talking about not necessarily cars, because there it could be seen as expensive, hard to store, etc. But in the long haul and heavy duty transportation, hydrogen can play an important role. And furthermore, in the topic of today, in solar fuels, when converting this to fuels like syn diesel or syn kerosene, combining with CO or CO2, then we have the opportunity to actually decarbonize the aviation industry as well. So these are sectors that can be transformed by the adoption of hydrogen should we move to more competitive solutions. Other sector that might see the impact of hydrogen, and we see it today, it's the adoption of hydrogen as a fuel in power generation, or how we can use hydrogen in power generation sector in different means, not only for power as an end, but heat as well. And we see it today, different companies looking into how to retrofit gas turbines by using hydrogen. So today, minor adjustments of existing turbo machinery can allow to firing up to 10% of hydrogen, some adjustments up to 30%, and major changes are required if we go above 30%. And the reason is that this, existing turbo machinery, as we know, can play an important role in, storing, if hydrogen is stored from renewables, then the existing assets that we have with adoptions or retrofitting can actually serve as, power supply back into the grid, besides fuel sources. With that picture, then I want to come to this one, which is, okay, how are we moving? Oh, I was kicked out.
How strange, because we haven't touched anything. Go back, please. Can you share again? Okay.
I'm back. Yeah, apparently. So I wanted to come to this picture where we see basically on the left where hydrogen comes from, and on the right where hydrogen can be used in the future. And what you see in red, blue, and gray and green are the different years. So 2019, or let's say today, to 2030 and 2050. And you see a transition of, the renewable hydrogen will increase drastically compared to how the brown and gray hydrogen will basically reduce, not as drastically as we would expect. And then in terms of adoption, transportation is a sector, and especially long-haul transportation, like I said, so will be the one with largest impact, as well as syn fuel for aviation and ammonia production or use in shipping. That together with the use of hydrogen in industry in some of the examples I mentioned. In the case of Sweden, the example of steel is not the only one. Here, I don't want to go through all of them, but I just tell you that how different companies from the refineries and chemical sector, together with companies from the steel sector, as well as from the agriculture sector, are trying to adopt the use of hydrogen by putting forward pilot projects that lead to biofuels, synthetic fuels, actual technologies for reduction of smelters for hydrogen in steel making, etc. So there are a number of applications that we can see in which hydrogen can serve, for decarbonizing the industrial sector, and companies are moving forward. This, all I said, is pretty much in line with the strategy that Thomas also mentioned. So by 2024, we're basically moving towards, okay, let's try to replace existing hydrogen production with renewables, then ramp that up to a large electrolysis processes and start to have new applications in steel and transportation primarily. And finally, by 2050, try to have penetrate all the different sectors using synthetic fuels as well. So from my talk was a big of an overview of what we actually teach, but I wanted to give maybe some key takeaways here, which is solar fuels can play an important role in decarbonizing the sector, especially transport and industry. Hydrogen is the most investigated solar fuel, but not the only one. There are many paths for producing hydrogen from the sun, and not just electrolysis. And I believe many others are needed and be more cost efficient depending on where we are and the resources available. Solar fuels are still costly, and it's hard to store hydrogen and transport it. And this is actually an opportunity for solar fuels, perhaps to act as a liquid storage carrier. And by 2050, with the current policies that we see from different compilations of studies, green hydrogen can reach up to 50% of the hydrogen demand, and might be not sufficient. And therefore, we need policies and awareness to drive the adoption and tax sustainably. Coming back to Marcelino's initiative, I think we need solar fuels now. I wanted to finish just with one example. What we do at KTH, or in my group at least, we are part of a large European project where we also look into a megawatt scale demonstration of how to integrate thermal power units with renewables. It's a large consortium, which I also try to bring to this initiative, of course, for sure, where we look into new components to make this happen. And in our group, we also look into different system analysis aspects, and what we see as in terms of future technologies, I think there's a large potential, a lot of focus on electrolysis, and a lot of focus in PEM, driven by the reduction of cost PV, but I believe that solar oxide electrolysis at high temperature combined with CSP can also play an important role there. And I just wanted to bring it here just to say that it can be very cost competitive, provided that, of course, a number of assumptions here are met. So with that said, thank you very much for the invitation, and I'll just, my email here for any questions. So.
Thank you very much, Rafael. I'm going to ask you to stop sharing. This was a very interesting presentation. You presented so many different options. I'd like to ask Thomas, please, and if I can, just 1 second, Valeria, we're going to have 5 minutes for questions, if I may. So I'd like to ask Thomas and Marcelino to come back. Just really quickly, we have a question for each, so I figure, why not? Don't worry, we have plenty of time. We'll get through the next panels, but I just want to ask these questions. So, if I may, first I'm going to start with a question from Julia Machado for Thomas, and it says, Thomas, thanks for the great presentation. Do you see the current hydrogen momentum benefiting the scale up of solar fuel technologies, whether it's a direct or indirect effect? So, Thomas?
Thank you very much for the very interesting question. And I think Rafael, with his excellent presentation just now, you really dissected and showed the interfaces, how basically hydrogen first is one of the solar fuels and what are also the interlinkages. I was reflecting a little bit on direct, indirect, and I mean, if it's not easy to define always, but I mean, if we would dissect it like in photosynthesis, light harvesting, light reaction and dark reaction, then for sure you have a lot of direct synergies when you think about sun harvesting to produce hydrogen, but also I think Rafael showed also with a lot of examples, basically, you would also, on the way to platform chemicals, you have a lot of, let's say, complementary research. Even if somebody would only start by hydrogen and then to the product, I mean, you would create whole lines of product lines or research lines in this respect also. A little bit difficult what is direct or indirect effect, but for sure, I mean, the hydrogen strategy is important also to look there. And also I would like to mention the energy system integration strategy, because I think what is important now, also with the importance and visibility of hydrogen, what is clear that we need to have carriers which actually can also transport between electricity needs and other energy sectors. And I think there are a lot of effect and synergies between hydrogen and other solar fuels. Thank you.
Thank you very much, Thomas. There's a question here that I think is for Rafael, but I think any of you probably can answer. This is why CSP?
Well, I want to clarify that. I mean, so CSP not the only one. I'll just say that I believe that high temperature, looking into short term, everyone's focusing to electrolysis. And I believe, yeah, you're right, PEM, alkaline electrolysis driven by PV, and that doesn't require high temperature. But if we look into a potential to go into higher cost effectiveness, solid oxide electrolysis at high temperatures can bring us some point there. And the high temperatures can be provided by CSP. That's maybe the point that I mentioned there. So these technologies complement each other, you know, PV, CSP, and the different electrolysis technologies that we have, besides the thermal options or the photo direct options.
And really, like, only the surface has been scratched. Like, everyone's talking about electrolysis like almost like the only option. You know, how do we build up electrolyzers? But there's so many things that we may be living on the drawing board that is actually potentially even better. Okay, so Pedro has a very interesting question that I'm going to extend to all of you, and then we're going to have to cut it there because unfortunately we don't have a lot of time for this. But he says, how do you see solar fuels now supporting the demand side for green H2? One of the main concerns for the current project industry developments and maybe taxes on CO2 emissions will not be enough to get industry to switch to green hydrogen. This is a good point. You know, it's not only about producing it. This is then how do you make the switch, you know, for people to actually consume it. So Marcelino, Rafael, Thomas, I'll leave it up to you to answer.
But I think that
Right
this is the challenge. We have now, from the point of view of solar application, you have many options to produce hydrogen and solar fuels, the thermochemical, photochemical, just we can use PV, electrical, and others. Of course, it's not clear what is going to be the winner or if there is going to be a single winner. So this is the reason we are all here now. But I really believe if we want this energy transition to happen, it's going to be through solar. And if we want hydrogen to play a crucial role, solar will be there. And we are here all to show this option, to also the concerns. I think Rafael also put very clear what are the barriers. And we need to all. But if you look at the past, many technologies were not available, and today are available. Even if you look at PV I started to work in 1999 in this technology. So PV was at the beginning very, very costly. And in the year about 2004 to 5, yeah, then the prices go down very quick. And in few years, the price was 10th of the cost 2 years before, and so on. So these things, you were talking to the people and say, this is not going to happen, and it happens. And also, again, with renewables, at the beginning, the people say, okay, these people working in renewables, they are mad people, crazy people. And now the renewables are cheaper. And this has happened. This is in my life and also in the life probably of all the speakers that are of my age. So I am very positive in this way. Okay.
Would you want to add anything, Rafael and Thomas? And then we'll cut there. There is a ton of questions, but I invite you guys if you want to stay and answer by text because we don't have any more time. Thomas, go right ahead.
Yeah, very quickly. I mean, also in the revision of the Fit for 55 package now, I mean, there's a revision on the regulatory framework for gas markets, and you might have seen also for alternative fuels infrastructure, which tries to really, let's say, accommodate all the needs to boost then the uptake of hydrogen, also to bridge to the markets.
Thank you very much. That's a good point, actually. This is going to change the game, I think, with everything that as we know it, once it develops and there is like a clear criteria. And Rafael, anything?
No, I think Marcelino and Thomas already mentioned all needed. So.
Excellent. So thank you very much, guys. Appreciate you sharing with us your expertise. I invite you, Rafael, Marcelino, if you're going to stay, answer those questions that we still have there by hand. And in the meanwhile, we have to move on to the next session because, obviously it doesn't end here. Next, we have a panel session with 6 speakers, actually. It's quite about making competitive solar fuels and their potential uses. So I'd like to ask Rosario Rodríguez from 𝗦𝗡𝗃, André Pina from EDP, Rafael, you're staying, and Taia from Lhyfe, and Philipp Furler from Synhelion, and Bilal from SOCAR R&D and Innovation, and of course, my colleague Carlos Marquez, who is going to be the moderator, to come on board and take it from here. So thank you very much, Carlos. I yield the floor to you now, and I'm going to try and help getting your speakers.
Thank you very much, Belén. And well, I caught the tail end of this conversation, which was very interesting. And I think, we'll be able to answer some of the questions that we have on the Q&A box in this panel as well. So, for those of you who are in the audience, sharpen your pencils and send in more questions because I think this is a unique opportunity you have here. You have representatives from different branches of technology, people who are making solar fuels, using different technologies, and a leading developer to like 𝗦𝗃𝗃 and SOCAR, which are run leading refineries, and Rafael as well here, representing the research and development world. So don't miss out on this chance to ask your questions whilst we wait for all the speakers. So let me see. I think we're all here now. So the way this will work is that I will ask each of you of the speakers to introduce yourselves, and then after the first round of very quick introductions, I'll ask you to make some kind of opening statement. And in that statement, you will let us know what you think is important from your point of view about the development of solar fuels. And well, it goes without saying, we've got a great audience today. And thank you to everyone who's joined us today. So, right, so let's start with the quick round of introductions. So I'll ask you as I see you on my screen. So, André, would you please briefly introduce yourself?
Hi, thank you, Carlos. Thanks, everyone. Good morning. Happy to be here. My name is André. I'm a director for hydrogen strategy and origination at EDP Renewables. We are developing multiple projects in renewable hydrogen across the world. Thank you.
Thank you very much, André. And Philipp, would you please introduce yourself?
Good morning, everyone. Thanks for inviting me to this panel. I'm Philipp Furler, the CEO and co-founder of Synhelion. We are a startup company from ETH Zurich in Switzerland, and we are developing solar synthetic fuels, mainly for long-distance transportation, especially aviation.
Thank you very much, Philipp. Rosario, please tell us who you are and what you do.
Hello, good morning. My name is Rosario Rodríguez, and I work as coordinator of upstream research projects in 𝗦𝗃𝗃𝗃, a Spanish energy company.
Thank you very much, Rosario. Taia, please, could you introduce yourself briefly?
Sure. Thank you very much. So I'm Taia Kronborg. I'm the Chief Business Officer and also partner of the company Lhyfe. So Lhyfe is a European company. We're started in France, but today we have offices all over Europe, actually also in Spain. And we are producing hydrogen, green and sustainable hydrogen. So that is really our core business. The only thing we do, nothing to do, no stakes in oil and gas, no stakes in everything fossil, just green hydrogen production.
Thank you very much, Taia and 𝗲𝗲𝗏, please, if you could briefly introduce yourself. And you are on mute, by the way. There we go. Now I can hear you.
Thank you, Carlos. Thank you for the invitation. My name is 𝗲𝗲𝗏. I am R&D and Innovation Company General Manager. State-owned company of Azerbaijan Republic is a major investor in Turkey and owner of the only petrochemical plant and one of the new refineries. And I have a doctor degree in chemistry, and I've been working for this company since 2007, and I've been involved in a lot of downstream projects. For last 2 years, I'm leading R&D company. Thank you very much.
Thank you very much, 𝗲𝗏𝗏, and once again, welcome to all our speakers. So as you can see a lot of experience around this virtual table. I think Rafael, think they know who you are because you just gave a presentation. But so we'll start with the opening statements, and I'd like to ask Rosario Rodríguez to start, please.
Okay. We all have a common ambition, 2050 with zero emissions. And how make it real? There are different players, European Union, countries, energy and technology companies, researchers, consumers. All of us have to take action. Energy companies are aware, and we have initiated a decarbonization route with the transition from fossil fuels to optimize renewable energies. In this transition, the solar energy plays an important role because of the low emissions and is the supply for manufacturing fossil renewable fuels. And currently, we are focusing on hydrogen. Refineries are traditionally major hydrogen consumers. And in the transition to biorefineries, we are becoming one of the biggest demanders of green hydrogen. Most of the energy companies are getting involved in the development of hydrogen industrial clusters that are being promoted by the European Union funds. And why not think big and convert CO2 into chemicals using solar energy? This and more can be achieved if all the players are well organized as a winner team, as proposes the initiative Solar Fuels Now.
Thank you very much, Rosario, for your opening statement. I think there is quite a lot to unpack there. Now we're going to go to the next person, who is André Pina. So if you could just let us know what you're working on and how do you see things developing.
Sure. So at EDP, we have established very ambitious targets for decarbonization. We aim to close our coal operations by 2025 and to be a pure renewable electricity producer by 2030. We recognize that renewable hydrogen and other e-fuels have a key role to play in achieving the full decarbonization of the energy sector, complementing electrification, and that's why we've created a dedicated hydrogen business unit. Now, we are mainly focused on the development of renewable hydrogen projects, but we do recognize that there's a whole value chain that needs to be established that goes all the way to the production of different e-fuels. And that's why we believe that in this nascent market, I mean, it exists for many years, but it's now really exploding and growing quite fast. There's a clear need for partnerships. And we're seeing that all over the world. We believe that partnering with other companies is a great way to expand the market and increase the adoption of these very important fuels to achieve decarbonization. Even though they are more relevant in the coming decades, we do believe that the work needs to start today. There's a long way to go in terms of education, not just and learning, not just in production, but particularly in uptaking these type of fuels.
Thank you, André, and we'll come back to the subject of partnerships, and all the how the public needs to be educated on the benefits of solar fuels after all these statements. But next, I'd like to ask Rafael Guédez to just share his thoughts. I know you're just giving a presentation, but
Yeah, I don't want to spend so much time because I literally talked for 50 minutes. But I think, like I mentioned before, there are a number of challenges that we need to all address, like Rosario just mentioned. And I think we are at the time to do it if we really want to make it happen by 2050 or even earlier. So, and I do believe that there are a number of technologies, not only electrolysis, that can make this happen. And also there are a number of applications that are not being seen now, for which we will need these fuels as well, besides refineries or so on. So with that said, then that's it from my side.
Thank you, Rafael. And yeah, that's a topic that will, I'm sure is of interest to everybody in the audience. You know, what could you use synthetic fuels and renewable hydrogen for? And, you know, what are the expected markets? We'll get to that. But first, I'd like to ask Taia Kronborg to give her opening statement.
Yes, sure. Thank you very much. It's really good to see that everyone wants to do hydrogen, and it's important. So just for the story, we created this company in 2017 for a reason. It was really to make a better world for our kids and our grandkids, because everything we emit stays in the atmosphere for a long time. So if you don't act right now, and it's really right now, 2021, it's not after 2025, it's not in 2030. So it has to be right now. So we are a company that's focused on doing. We already have a plant operational, so it's not just pictures on a, on a website. We have 40 megawatt operational in 2023, and I have €500 million to invest in plants before 2025. So that's really, we focus all our energy on that, and I hope everyone here is aware of that and will also focus the energy. We are, like André said, convinced that it's not just one company who has to do it, it's really everyone. Because if everyone is not jumping on the train, it's not going to happen. So really happy to see that you guys are all involved. We definitely want to be part of this and are pushing very hard to make it happen as fast as possible.
Well, thank you, Taia, for your enthusiasm as well. I see that you're ready to hit the ground running, with plans and everything. And we'll definitely keep an eye on how your plans develop as well. Well, next, I'd like to ask Philipp Furler for his opening statement.
Hello. Thanks, Taia, for your statement. I fully agree. So we at Synhelion, we use concentrated sunlight to convert water and CO2 in thermochemical processes to syngas and then into synthetic fuels. So we use CSP technology because it's a source of very cheap high temperature heat, and we can use cheap thermal energy storage to operate the system, the whole production chain 24/7, which allows us to achieve acceptable and competitive production costs. And so I see a world today where with a lot of talking, with a lot of PowerPoint slides, only few companies are putting the technology on the ground, as Taia said. And this is really what we need to do. We need to put the technology on the ground and roll it out, scale it up, and produce hydrogen, produce fuels to really change the world. Energy transition doesn't happen with just talking. It happens with heavy equipment which you need to put on the ground. We are installing now, I'm now on the site in Germany. We're installing now a reactor which is 6 meters tall, 12 tons heavy. It's really heavy equipment which is needed. And I'm extremely excited to roll it out and to see other companies doing the same.
Great, thank you, Philipp. So, well, it'd be look forward to seeing the reactor once it's installed. I'm sure it's a sight to behold. And well, and in the closing the round of opening statements, I'll ask 𝗲𝗲𝗀𝗴𝗏, please, to go next.
Thank you very much. So we know that it's crucial today to accelerate and support technology innovations for clean energy transitions to achieve reduction in carbon footprint and secure sustainable energy source in order to meet the goals of Paris Agreement. And 2 months ago, Turkey has ratified the Paris Agreement, and as a major Turkish investor, we are also now committed to these decarbonization goals. So, it's very important for in making clean energy and efficient development, commercially proven technologies. R&D and innovation is very important. It's a main actor and it's also driver. So, as most of R&D companies, we are also committed and working and also pursuing each collaboration opportunity to develop more sustainable replacements for refinery and petrochemical feedstocks and products. So we have initiated a lot of strategic R&D programs, and for next year also we have budgeted several R&D projects related to solid oxide electrolysis, also PEM electrolysis, also for usage of concentrated solar technologies for process heat. So however, we know that it's a challenge to compete with currently with existing technologies, but we believe that in near and future it will be achievable to with different support initiatives and also regulations, it will be possible to achieve. As far as concerns SOCAR, we put special emphasis in investing in clean energy and energy efficiency. One example is our onshore wind farm with total capacity 51 megawatt located in our refinery petrochemical facility. We also have a world-scale brine electrolysis unit, and approximately over 50% of this renewable energy equal to the energy used for production of hydrogen at this electrolysis unit. So we are aware renewable energies and also world-scale production of hydrogen at electrolysis unit. What can finally add that renewable and fuel energies will become compatible with their fossil counterparts in the near future. So we need to do our best to develop and accelerate this energy transition. Thank you.
Thank you very much, Bilal, for your statement. So well, I think now we'll have about an hour or so of conversation, and what I'd like to do is to make it as interactive as possible. So if you are there in the audience and there is something, clarification that you need, just pop your question in the Q&A box and we'll get to it. But I'd like to start with a question that I think it's is probably one of the most important, and we all know that a solution needs to be found to the issue of carbon emissions in fuels and in chemicals, but they still, at least last time I checked, I don't know what it looks like now, that renewable hydrogen was between 2 and 5 times more expensive than grey hydrogen, i.e. red. So definitely those costs need to come down, although with the prices of gas now, I'm not sure actually, but these costs need to come down. And so how could this happen? How could the production be optimized to bring the cost of renewable hydrogen down significantly? And maybe I should open the floor first to the people who are producing renewable hydrogen and synthetic fuels here, and Philipp, since you have your microphone open, I'll ask you to start answering this question.
So first of all, we are mainly focused on producing synthetic fuels, but certainly one key ingredient is hydrogen. For us, the key aspects for achieving low prices on one side, the energy input, which needs to be cheap. So you need to have a cheap source of energy. In our case, that's high temperature heat, which is probably one of the cheapest renewable energy inputs you can get. And then you need to find a way to to provide this heat or energy continuously to the process, because those plants, from my perspective, need to be operated 24/7 for many hours a year, let's say 8,000 hours per year. in order to use the equipment efficiently. So in our case, we are using a thermal energy storage, which allows us to store part of store that solar heat which we generate during the day and deliver it continuously to the process 24/7. So operating the chain continuously. So cheap renewable energy input, cheap storage technology to operate continuously, and then third component from my point of view is scale. So you need to scale it up to a reasonable size, especially for synthetic fuels. You have some components like the fuel synthesis or Fischer-Tropsch synthesis, which needs to be operated at a certain scale, and then you achieve competitive costs.
Thank you very much, Philipp. And I'd also like to know Taia's view on this. So I'm sure that you have, you also have thought a lot about these issues.
Sure. So share a lot of your views, Philipp. It's very simple, actually. You need to reduce OPEX. So OPEX in this context, when you produce hydrogen, it's almost all the electricity. You can have 75% of your hydrogen cost, which just comes from electricity. So of course, you need to have cheaper electricity, which is really a good thing, because solar electricity can be very cheap in some areas. Second thing, you need to improve the efficiency of your electrolyzers, because when you improve the efficiency, you actually use your electricity, which is your biggest OPEX cost, in a much better way. And that's on the OPEX. And secondly, it's really on the CapEx. You need to reduce the cost, not just of the electrolyzer, but of the whole thing of setting up a hydrogen production plant, because everyone has what would you say, does the mistake of saying, okay, so electrolyzers cost this, then that's what I take in my business plan, and this is what the project will cost. But it's not true. It costs much more, because you have a lot of other things to do. You need to do all the permitting. There's a lot of engineering. There's a lot of things. So there is a big technical challenge also in order to make this much easier to put in place, to scale up. And of course, building many plants, building out the capacity of electrolyzers. Because today, if you go and visit the electrolyzer manufacturers, they don't have gigawatt capacities. They've never manufactured this. Today, it's like 100 megawatt, which is sold every year in the whole world. It's very small. So these are the things that needs to be done. And I would say that the last thing on the storage, it's definitely true. Not an easy thing to deal with. Comes with making flexible processes. So maybe you don't have to have a very steady inlet in your sustainable fuel. Comes with actually building hydrogen grids and so on, where you can have large scale storage, and making downstream, which are easier and cheaper to store. Oh, last thing is also de-risking the project, because this is very technical and but you also have to finance your projects. And then you go to the bank and you say, okay, I would like to finance this project. And they say, where are all your offtake contracts? How risky is this? And you have a cost of financing a project, which is more expensive when it's very risky, and which will get less expensive. So really making the whole project solid with offtake contracts, with technologies that work is also a good thing to get prices down.
Thank you very much, Taia. I think you've touched upon all of the issues that we'll talk about in this session, and I think that you mentioned a couple of things that have to do not just with the technology, which is obviously very important, but also about project development. And since we have a project developer in the room, I'd like to ask André really for his views. So what do you think? Could you elaborate on how do you tackle some of these challenges that Taia talked about in bringing down the cost or operating as efficiently as possible to deliver hydrogen cheaply.
Yeah, I must say that I'm very much aligned with what Taia just mentioned. I mean, she covered a lot of topics. From our projects, what we are looking at is really understanding the full value chain of the project. And so we start developing a project already looking for the off-takers for that hydrogen, because as Taia mentioning, understanding where the hydrogen is going is really important to de-risk all of the project development and make sure that the cost that you are incurring actually makes sense and will be fruitful. We mustn't forget that hydrogen is not really a liquid market, right? So knowing where you're going to place your product is key to develop any project. The other thing that we are really working hard on it is understanding where are the risks of the project. You have investment that you make on CapEx for the electrolyzer and all the systems, and they are quite significant, as I mentioned. But the renewables part, where you can have a lot of risk, that's a liquid market. And so the way that you size your renewables, supply electrolyzers, and the way that you think about the risk that is involved in that investment, it's a little bit different in how you work on designing the hydrogen project itself. So there's a few ways that you can reduce the cost associated with renewables. You can, for example, oversize renewables in order to be able to supply your electrolyzer with a more stable profile, reducing costs, of course. But if you really need to work it as a 24/7 load, as we were mentioning, then you will for sure increase your electricity costs. So there's a sweet spot there that you need to find that will vary from project to project depending on local characteristics, and that you will have to play around with your renewable sizing, your electricity storage, your hydrogen sizing, and your hydrogen storage. Okay, so all of this, we are looking at all of these components really to figure out what's the best way to supply hydrogen to a specific end user, because that's what we want, really, to supply hydrogen to someone that has a set of characteristics that need to be met.
Thank you, André, and I think all of those issues are really important, and it's not just about producing the hydrogen, but actually delivering it. And we have representatives from 2 companies here, which are large hydrogen users. So maybe it would be good to hear from them. How have you thought about these issues? If you have thought about the issue of how the hydrogen is delivered to you, how much of it you need, and when. So Rosario, I think see you
okay.
unmuted your microphone. So.
Okay. The hydrogen should shift to green hydrogen, and I think that is an important policy to promote these actions. In fact, Europe has the target to become neutral in carbon by 2050. This establishes policies to increase the renewable energy. All the countries are committed with the Fit for 55 package. The energy companies are committed, and we are doing estimations in a scenario where the hydrogen will become green hydrogen for the future. And in this route, we have to use renewable energies, and with this goal, the total green hydrogen by 2050.
Great, thank you. Thank you, Rosario. What about the work that you have been doing, Bilal, in this at SOCAR? What are you thinking about in terms of how much hydrogen you may need and how it will be delivered?
Thank you for the question. For our industry, amount of required hydrogen is very huge. So we have natural gas-based hydrogen production. So we are also working and planning related to converting this hydrogen unit and maximizing the production of blue hydrogen. But unfortunately, there are it's not easy to achieve. We need to have some capacities for that. But in parallel, we are also investing some in different projects of continuously converting CO2 to some valuable chemicals. Especially, we have financed projects, EU projects related to capture and also utilization of CO2. With academia, we are also working on CO2 one-stage production or catalytic production of DME, which is very valuable and low fuel, which can be replaced diesel. So also we believe that decreasing the cost of solar electricity and also capex for green hydrogen will be create additional opportunities to accelerate this energy transition, especially for huge energy consumers, especially for steam crackers and other major units as hydro crackers and also hydro treatment units of refinery. So we're also working on as I mentioned, decreasing capex of CO2 capture and also unit cost improvements in CO2 capture, and additionally material cost and durability for some thermochemical cycles. So as my colleagues mentioned, it's reach lowest possible cost is very important, and cost of renewables should be decreased, and the cost of CO2 capture from air and flue gases is also very important for accelerating this process. Thank you.
Thank you, Bilal. And I don't know whether you have mentioned, all of you, a number of things, and one of them is that producing low cost hydrogen is not only a matter of increasing the number of hours that your electrolyzer or your equipment operates. It's also about the cost of electricity, and there is a sweet spot there. So which I think is a different mindset from production of many other things. So Rafael, I don't know if in your research, if you have seen some work on where this the sweet spot could be, and how you could combine, how could you manage the variability of renewable energy to have still an efficient production process?
Sure, and I think, all of the speakers here already mentioned different aspects connected to this, but to increase to increase the cost efficiency or optimize the production costs, and like André mentioned, you are not in isolation only when looking into production. This is a full integrated system. So looking into how the subsystems interact between each other is very important. But then if you even look into the components, the subsystem itself, like looking into the, let's say, specific electrolysis or thermochemical production, or thermochemical solar field with reaction, then looking into larger scales will help reduce the cost, proving the reliability of the technologies, avoiding inflexible operation of the electrolyzers, for instance, or some of the reactors, because we're not there yet. Looking into high efficient technologies with a lower TRL might be an opportunity to also decrease cost in the future. And then the point of the capacity factor, you're right. In our studies, for instance, the most competitive, from a theoretical study, electrolysis-based production would be basically don't put any storage, but is that even feasible, right? Just use PV and electrolysis. Is that even feasible? No, you have a unit to operate, which is not inflexible. Then you have a trade-off there with CSP-driven electrolysis, where mainly the sweet spot is at a very, very high capacity factor, because then is where you reach them. But then does the user requires that, right? So then it's always looking into the full picture, and every user needs will also vary.
So I think this is one of those cases where I think, as all of you have mentioned, it's like, well, it depends, and it depends on many things. Where your project is, the cost of electricity, and even the what regulations consider renewable hydrogen or renewable fuel. But we won't get into that just yet. I think I think there are quite a lot of things that could be done with renewable hydrogen and with solar fuels. And Rafael, you mentioned some of the projects that that are being carried out now in Sweden and elsewhere to decarbonize industry. So I'd like to hear the views of like everybody else in the panel. So what's the role of renewable hydrogen or renewable synthetic fuels in decarbonizing industry? I don't know who'd like to go first, but not all at the same time. Taia, would you like to go first?
Sure. So for industry, if we're looking particular at industry, definitely where you have the use today, so chemicals, steel, that would be a great thing and an easy switch in some sense, So at Lhyfe, we don't work together with the refineries. It's just a basic rule for us, because we believe and we hope that the refineries, sorry if there are some refineries here, but that they will close in the end. So because we would like to have fuels which are not based on fossil fuels. So, but all the other things, ammonia, methanol, steel, where you today really use gray hydrogen, it's a very easy switch. And then you can ask the question for other industries that use gas today as heat, not as a process molecule. And here we're talking about cement, glass, and lots of other industries which have a huge need for heat and which actually burn gas today. And in this context, if there is a way of really reducing the CO2 emissions, why not? But you should go first for electric if it's possible. Use all the electrical, the electrons, the green electrons that you have in the absolute best way, and use hydrogen for what you cannot decarbonate in another fashion. So I think that would be, there is a huge potential of really decarbonizing with hydrogen, and we would go in that way.
Great. So any other views here? So I can imagine, Philipp, that you are producing synthetic fuels. So you have studied the market really well. Who will require synthetic fuels, and I'm sure. So what are your views on this?
I mean, our view or our target markets for synthetic fuels are mainly transportation over very long distances, sectors which cannot be electrified or which are very hard to electrify, especially aviation, long distance transportation, where the energy density of a hydrocarbon is essential. For industrial processes, I believe Rafael gave a very nice overview where the potential is, especially steel or refineries where the hydrogen can be used directly. For other industries like cement, I believe synthetic fuels are too expensive to just produce heat. So there we have a different approach. We replace the burning of fossil fuels by solar heat or by using green electricity. So we are partnering with Cemex, one of the largest cement producers in the world, and we are developing jointly a process to produce solar cement. So we are replacing the burning of fossil fuels to drive the process, so to generate heat by cheap, high-temperature solar heat, thereby cutting down net CO2 emissions of about 40%. And you're left with the intrinsic CO2 emissions from calcination, which you cannot avoid if you produce cement. And there is the connection. And this CO2 can be quite interesting for producing synthetic fuels, at least in a midterm scenario.
Great. Well, that sounds like a really interesting project that you're carrying out there. And you know, we've heard from all of the different applications here, but you know, I suppose that the ones that we'll see first are those that are related to replacing grey hydrogen from existing processes, right? Things like, well, like refining, fertilizers. Do you agree with me on that, or do you think that, you know, there are other things that will come first because maybe it's more competitive? I don't know. Maybe let's get someone from one of the refineries to say something. So Rosario, what do you think? So, you know, are you planning on replacing hydrogen?
Yes, sure. The hydrogen is an important pillar of the decarbonization in refining, because refineries are major hydrogen consumers. And in the decarbonization is based on the substitution of grey by green hydrogen. And this is possible because the hydrogen contributes to the greenhouse emissions, but in the case of the biorefineries, this substitution is going to be promoted for the next 30 years, and is based currently in the use of the electrolyzers that are becoming day by day more efficient, and in the combination of the capture of the CO2 emissions. And there is a high room of improvement because not only we are going to use the current technologies that are based on the electrolyzers that are currently we use, but also all the improvement in this kind of equipment is going to help the industry to decarbonize.
Thank you, Rosario. And you know, Bilal, you also, I know you're on the R&D side, but I'm sure that you must have given a lot of thought on what you will use the hydrogen for, green hydrogen, hopefully for a lot of things. But you know, what have you? What are your thoughts on this? What is the main use of hydrogen, of renewable hydrogen, at a company like SOCAR?
Thank you. As my colleagues has already mentioned a lot of principal and critical parameters, and I would additionally say that hydrogen, you know, fuel is particularly critical for reducing emissions, especially in the hard to decarbonize sectors in which direct electrification is difficult to implement. So downstream sector after steel and cement industry is a major carbon emitter, you know, and so we also have some targets at the first stage up to 2030 to decarbonize to the 40%, and additionally to reach optimum level till the 2050 year. But there are a lot of things that should be implemented, and as I know, we mentioned about the hydrogen role in this decarbonization strategies, but it may be used for the production. We believe that for the production of synthetic naphtha or methanol, also in the plastic industry as well, for synthetic fuels for long distance transportation applications, is a strong candidate, I would say, for mixing with natural gas as a hybrid fuel for the near future. But I believe that, and you will agree that green hydrogen can be commercially competitive only if it comes down to the same unit production cost with gray hydrogen. Of course, this can be achieved both with the reduction in capex and opex and with the government incentives and regulations like carbon pricing. So, for example, I will make some calculations. I would say that if green hydrogen delivered at €2 per kilogram, it can compete with gray hydrogen at a price of €100 per ton of CO2. So it's for making some comparison. So we need a lot to do. A lot of things. Thank you.
Great, and I see that I think that Taia, you look like you want to add something to this. So
yeah, I really think that we should start paying exactly for what we get. So, for example, it's not normal that you can get in France a kilo of apples from New Zealand in winter, and it only costs 1.5 euros. And it's not normal either today with what we know, that the fossil fuels are not more expensive, or that we don't have higher CO taxes because it is so important to reduce, and it has a so big cost without, on the outside. So I think we will find, I hope we will find really the breaking point where what comes from fossil will be more expensive with CO2 taxes or other incentives, and where we also might see increase of some prices of some different things. It's what will happen in order for us to make it sustainable.
So do you think, if I get you correctly, that you need to, well, one of the policies that may be required are those that put a higher price on carbon emissions?
Yes, definitely. I mean, that is it's something which is needed in order for all the green to really take up. It would be one of the strongest things. Look at the US. They just announced 3 euros per kilo of hydrogen in tax reduction if you do this green hydrogen. So there are many incentives which are possible in order to really make green hydrogen happen.
So I think between you, Taia, and Bilal, you mentioned a few important things there. One of them is that, well, Bilal as a big hydrogen consumer was saying, well, for renewable hydrogen to really take off, it needs to reach cost parity with grey hydrogen. And you mentioned, Taia, that one of the ways to achieve that is to actually increase the cost of CO2. So I'd like to ask other people around this table, what would need to happen at a policy level, or what would need to happen really for renewable hydrogen to be able to displace grey hydrogen?
If I can jump in on the conversation, I think,
please.
We need to look at this from establishing a level playing field. It's not just a matter of making something more expensive. We need to make sure that technologies can compete at a similar level. And if you really start to look at how you can develop a grey hydrogen project and compare it with what takes you to develop a renewable hydrogen project, you'll see that as of today, we are not yet at a comparable level. I'll give you an example. For example, in Europe, current grey hydrogen production receives free CO2 allowances. Okay, and if you look at renewable hydrogen production, which incurs in electricity costs, electricity is part of the EU ETS. So even if you do a renewable PPA, the implicit price of carbon is included in the price of that electricity. Okay, so to produce renewable hydrogen, you are already paying ETS. Okay, in order to make this a level playing field, you would need to have the exemption of the EU ETS, and you would need to have the free allowances. Okay, and this is something that, where is the free allowance is being discussed. The exemption from the carbon price, it depends on member state, it depends on local policy. Other examples is, even in the development phase of the projects, we are still lagging a lot. And you compare, for a lot of permitting and licensing for renewable hydrogen projects faces the same hurdles as a grey hydrogen project. and they are not the same. They are different technologies, they have different impact. So all of this is a learning process that we are seeing that even the national governments are taking, and they are really figuring out what's the proper regulatory framework to allow renewable hydrogen projects to take place. Okay, and this is just a few. For example, I could continue and say the importance of sectoral integration that electrolyzers have, and having proper ancillary services markets for the electricity sector is critical for electrolyzers to get additional revenues that can lower the cost of the other product that they produce, right? Because this would be another product that they will sell, and the list goes on and on. And this is not just about renewable hydrogen. Of course, other e-fuels, they are still facing similar hurdles because everyone is learning. Okay, so I'm sure that there's a lot to do in the coming years to establish a level playing field, not just increasing costs.
Yeah, I mean, there is so much to do that, to be honest with you, I do not envy the situation of the regulators, even because, I mean, you mentioned the ancillary market service, and I was at an event in Spain. Well, we organized a few weeks back, and they were saying, even then, there are a lot of things that are not clear, and like, just to give you an example, a big one. You can't really have a standalone battery. It needs to be connected to a renewable resource. So imagine, how, if I may, how much more complex it would seem now to actually put the electrolyzers in as well, to incorporate them in their ancillary services. But I would like to hear the views of others, around these tables. What would need to happen for green hydrogen to really take off? And I see Philipp has his hand up. Go, Philipp.
So, yeah, I agree. So level playing fields are certainly important, and carbon tax to be competitive on the long run. But I think it's simply not enough to roll out the technologies. In the beginning, they are much more expensive. So just the carbon tax and the level playing field will not allow you to roll out the technology. So it needs more. It needs support from governments to reduce the risk of installing, so reducing the risk to bring the technology on the ground, to implement first projects, gain experience, gain confidence, especially with investors and financial markets, which then allow you to scale up, to reduce costs. And then in the long run, if you have the right carbon tax in place, you will be competitive. But this doesn't happen from day one. Then my other point I want to make is, please don't shut down the refineries, but switch from fossil oil to synthetic oil. So we can provide you synthetic oils, and we need refineries in the future to produce the sustainable jet fuel or diesel or gasoline. So this capacity is still needed.
Sure.
Thank you. So I don't know. I think Rafael, you put your hand up as well. So
yeah, very briefly. Actually, it was along the same lines of Philipp. I think from a policy perspective, you need let's say different axes. So one is on the regulation on what happens with CO2 and the taxing and maybe capping the amount of CO2 each industry can or is allowed to have, etc. But I support Philipp. I mean, the other very important one is incentive on the production side, on that technology adoption, technology reliability. We saw it in the PV or solar. I mean, feed-in tariffs before. Now we are in PPAs, right? But before we had feed-in tariffs, otherwise we would not be here, etc. And at the same time, policies are needed also for market regulation and infrastructure development, which is also very important. So that's along the same comments as Philipp.
Thank you, Rafael. Rosario, please.
Yes, now we have a good opportunity because of the European funds, the Recovery and Resilience funds, that want to invest in climate change mitigation. I think that there is room to invest in this transition. So I think that move from gray to green hydrogen can be funded with these recovery funds. Is in the future scenario, the electricity cost will be cheaper, so the electrolyzers can benefit of this new market, and it will be positive for the green hydrogen. And I think it's a very good opportunity for refineries to move to biorefineries.
Thank you. Thank you, Rosario. And you know, there are actually quite a few questions here from the audience, and one of them talks about the false starts that we've had with renewable, well, with hydrogen before. So I think it was, you know, just a child at the time, but there was, I think, you know, 30 or so years ago, there was a big push for hydrogen, and it didn't quite happen. And there is, and Fernando Oliveira here is saying that, you know, he hopes that this time it will become available. So, you know, what is different this time from the previous times that we've looked at hydrogen as a way to decarbonize? And I think Rafael wants to go ahead.
Yeah, I'll just briefly, and I think I mentioned it in this presentation I had earlier, but I think some of the key aspects, and of course, I wasn't myself so active back then in the previous hype of hydrogen, let's say, I was very young. But I see what I've seen from literature and what's in research is that compared to back then, not only one key differentiator is that renewables today are cheaper. So regardless of that, so, you know, we are reaching cheaper costs in the LCOE from solar, wind, etc., and also in the electrolysis part. So that's one important thing, so technology. But the other very important one is, you know, this decarbonization goal. So far we've been complaining on that policy is lacking, but at the same time, we've seen at least some action. So there are goals now set at national levels, at regional levels, etc. And to meet those goals, then the actors are making aware that, you know, there are a number of solutions that need to play, and hydrogen can play an important role there as a vector. And then these actors before, it was mainly, you know, the state or particular researchers pushing for that. Today, we see it here today in the panel. It's also industry, which was lacking before also. So industrial actors see the need to change the way they approach their consumption today, fossil fuels, because they might also suffer from this in the future. They need to change from a policy point of view and not be reactive. So that's my take on how things are different.
Thank you, Rafael. Anybody else on this table would like to take a stab at answering that? So, you know, why are things different now than they were the first few times that we tried to push hydrogen? I'll be honest with you, I don't know the story that well, so I don't even know if it was renewable hydrogen. But I think, you know, a key thing now is actually this government support and all of the funds that are behind the renewable hydrogen development. But you know, going back to the theme of policy that we were mentioning before, and which is one of the key aspects of making renewable hydrogen competitive. I was at a webinar a while ago, and one of the panelists is an international developer was saying, well, you know, I think that in Europe there is a danger in Europe that the conditions for labeling hydrogen as green are too restricted, and he was referring particularly to additionality and simultaneity. That's even a word. So, what are your views on these? You know, are these conditions necessary, or are they for the sake of making everything like absolutely renewable? Do they threaten to stop the or to slow down the development of renewable hydrogen? Don't know, not all at the same time. And André, sorry, you are the big developer here, so.
No, sure. I was thinking, I mean, there are a lot of risks that we are facing in the development of renewable hydrogen projects. This is this is key. But I'm trying to figure out a nice way to say. But I mean, as I mentioned, I think we need to understand what assessing risks properly is critical. Assessing the impact that this type of projects have is also critical. This includes not just understanding the conditions that we will be requiring, the impact that we are going to have, the integration that we are going to have with all of the sector, and don't forget that we are bridging to different sectors. And for example, we're seeing a lot of discussion on potentially what role can actually renewable hydrogen play, given that the constraints, given the conditions that we require to produce it, in terms of water, in terms of land, in terms of all of this. And these are risks that we need to manage, and we need to understand if they are available, what type of infrastructure do we require in each location, what type of trade flows we are going to require. So all of this is new, and this is not entirely clear how we're going forward. It's clear to us that we need to go forward. So we are doing our best to develop these projects and really integrate with the off-takers to make sure that we have all the conditions. But yeah, not a very straightforward answer.
No, I think it's not a very straightforward problem, really. So, you know, it's you know, I understand that there is not one answer, but Taia, I'm sure that you have thought about this as well. So,
Yeah.
you know, the people you are talking with, you know, how do they see these
Sure.
these requirements? I mean, you know, obviously it's easy for me to say because I'm not
Mhm.
developing anything, but when I look at a requirement for all of the requirements at a place that has, you know, not that good, well, or not ideal renewable resources everywhere, I think, well,
Yeah.
you know, it's going to be difficult. So
Yes, you really at some point add a lot of boxes to tick. So that I agree really on that with André. But I think so it will be a process, and there will probably be a period where you kind of test and learn a little bit. But what we need to avoid is a little bit how the electricity market works today. So I can, you know, in France, where we almost have only nuclear electricity, almost all of the electricity offers are green. And I can make hydrogen today by using guarantees of origin that I buy from Iceland, let's say, from Iceland or from Norway, which is produced in the summer when you have sun all the time, and I will use it in November. And that doesn't make sense. It really does not make sense anymore, because then in France, where I produce, I know that in November, where my plant is located, there are lots of gas around, and especially all the times when it's very, very cold, I am sure I will use a very carbon intensive electricity. So those are things you cannot do anymore. So the feeling I have is that now the regulations are getting much more stringent on how you qualify green electricity and how you qualify the green downstream. Afterwards, I think, again, there needs to be a period of transition, because it's very difficult to synchronize exactly when you put in place electrolyzers with when you put in place the energy assets, because it's not the same time of development and so on. So there are some hurdles still to be made. However, we really do believe that there should be more, how would you say, harmonization in how, when you put in plant when you build your electrolyzer plant, a huge electrolyzer panel plant, which will use a lot of the electricity, you kind of need to ensure that the electricity you use has a positive impact in the end and will not degrade all of it. So not a very straightforward answer either. And I don't have the answer. Everyone is kind of going around and toe tipping on this, because it's a difficult question to answer. And I think it will be an evolving thing. When you start today, like, again, everything is difficult. The technology is not completely ready. And when you have many things to tick, it just gets a little bit more difficult. But you need to see it in going towards something where you can really say my electricity that I used was green.
right, and well, you know, thank you for those answers. I know it's not an easy question. You know, there is something else going on in the market now, which is gas prices seem to be high. I don't think, I don't know how long they're going to be high for. If I knew, I probably wouldn't be here. But how does this affect the deployment of renewable hydrogen and synthetic fuels? From as a when I first look at it, I may think, well, it might be good, right? Because that makes raw material that you make gray hydrogen from more expensive. But I'm sure it's a lot more complex than that. So, what's the impact of high natural gas prices in Europe now on this on the development of this sector? And
maybe I can start. From our perspective, the influence is not so big. I mean, certainly variability now in fossil fuel prices drives a bit the transition to synthetic alternatives or clean alternatives. But our key customers, like large airlines, they're really they see the synthetic, or let's say advanced biofuel alternative, really as a different product. This is not the same. I mean, this is just a different type of fuel, which they want, and which policy also imposes at some point that they reach a certain quota, that they buy a certain amount of such fuels. So it's not really in competition directly. So increasing gas prices might push a little bit. And one important aspect which I wanted to mention before, I think it's really for a producer quite critical to select the product which you are producing or the application carefully. From my perspective, the closer you go to the end customer, the higher is the willingness to pay more, because it's not only policy, it's also the people who want to have such products, clean alternatives, clean products. It's the storyline behind, and certainly the impact you create. So I would say hydrogen for a oil refinery is not a very sexy product to sell, but if it can go closer to the end customer for a mobility application or something like that, then the market might be willing to pay a much bigger premium.
Great, thank you. And one of the, I see two hands up. So I think Rosario, please go first. You are on mute, by the way. So.
Okay, sorry. I think that the high gas natural gas prices may make more competitive the green hydrogen, because the renewable electricity may be more competitive if the natural gas increases. That is the raw material for the gray hydrogen. And so in this environment of prices, the competitiveness of green hydrogen is better, in my opinion. And it is something probably geopolitics, because of the problems of in Russia, the forecast of a cold winter, and this has made the increase of natural gas for 30 to 90 euros per megawatt, and that is the raw material for gray hydrogen. Probably the competitiveness is better. Mm-hmm.
Great, thank you, Rosario. And Bilal, I see you had your hand up as well, so please go ahead. And you're on mute as well.
So your question related to the latest prices. So high natural gas prices enable green hydrogen produced under power purchase agreement to compare with the cost of gray. So we have recently be able to see some reports and comparisons provided. Of course, the technology has to be there to make a real-life comparison, but the numbers look promising. However, that also shows that PPA and some similar incentives are needed to keep renewable hydrogen competitive for the short and mid-term.
Thank you. Thank you, Bilal. And see, Rafael, you had your hand up, right? So,
yeah. So I just want to comment, I think, and we see it from the answer here on the panel as well. So I think that the point of natural gas price is not the one driving the green hydrogen adoption. So on that point, I agree with Philipp. And then what you see more the impact like on the actual users today, which are refineries or ammonia fertilizers, they might then consider the option based on cost. But most of the end users are adopting green hydrogen or synthetic fuels, not primarily because of cost compared to natural gas, but because they want to shift, like Philipp mentioned. So this is not something that I see as it could be some kind of maybe transition now, something happening now, but it's not something that will drive the thing here. We're talking about something bigger.
Right, and well, that's a very good point. And if you look at the broader environment as well, and this is actually related to some of the questions I see here from the audience. There are it seems that the prices of everything is going up. Like prices are going up across the board of all raw materials. How does that affect or could that affect the deployment of renewable hydrogen and other and synthetic fuels? I think probably ask you, Taia, to start answering that question. Is that something that?
Yeah, it sucks. So it really isn't easy to cope with, because right now when you buy an electrolyzer, it's more expensive than 6 months ago. That's just the basic thing. How I would say the most critical is probably not the capex, but it's also that the current very high gas prices are also driving up very much the electricity prices, which are at a level never seen today. So that is, I would say, what is the most critical right now. In order to have these projects up and running.
Thank you, Taia. What about you, Philipp? How does the current environment, affect the deployment of synthetic fuels in your view?
We take maybe a bit of special approach. We design our systems to be grid independent, so we do not require any electricity from the grid, and this turns out to be quite a strong advantage. So we produce all the energy we need ourselves, and we can independently scale. And we go into areas where we don't compete with food production, where we have lots of sunshine, like deserts or desertic areas. And we produce this high energy density hydrocarbon, a synthetic raw oil, which we then transport to a local refinery where the certified products are produced. So for us, I would say that the current environment of uncertainty in power supply is more beneficial than hurting. So it underlines the advantages of our technology.
Great, thank you, Philipp. Well, if no one else wants to answer that question, Bilal, your hand is up. Would you like to add something, or was that by accident? You're on mute as well.
By accident.
By accident. Okay.
Yeah, maybe I can take the opportunity then, just to.
Yeah.
I think there's a path that we are taking in the hydrogen field that we've taken in the renewables before, In many countries, many regions around the world, we already have long-term contracts for the sale of renewable electricity, and that protects you against this volatility of prices. The European market is really not so hot yet with this type of agreements. There's the industrial users are generally much more risk averse in establishing these long-term contracts, but once this gets rolling, I think this is a key advantage for renewable hydrogen and e-fuels, in the sense that you get a much more stable production cost, and so you are protected against all of this volatility. But it's a path that we really need to start making and start walking.
Thank you, André, and well, we are coming, towards the end of our allotted time, so I think we have one more question we could answer. I'd like to ask you what kind of innovations are we likely to see in the next 3 to 5 years that could have really make a dent on making fuels such as hydrogen and synthetic fuels more competitive. So any innovations in the horizon that we should look out for, and look forward to, I suppose. Rafael, I see.
I will reply since I'm the one from research, but
yeah.
I would say that I see a different perspective here. So in the very short term, so you asked your question 3 to 5 and even 10. In the very short term, I believe to push it to market, probably enhance operational flexibility of the existing alkaline or PEM technologies for electrolysis. Try to increase power density of these technologies, ramp up technologies that help them industrialize them or ramp up production of these technologies will help them decrease cost. Now, moving more into the 5-year perspective and how to make them cheaper, I think we will look into reliability of higher temperature electrolysis, or start to look already into the reliability of thermochemical option or paths, and even beyond 2030, so 10 years from now, the photo roads as well, and yet to be proven. So.
Thank you, Rafael. Philipp, I don't know if you'd like to add to this. I won't expect you to reveal all your secrets, but what could we look forward to in terms of innovations that could drive down costs and make your synthetic fuels more competitive?
Yeah, we have pretty cool technology in the portfolio to reveal, but I don't think we need more technology than we currently have on the market. We need to roll it out now, and this will allow to reduce cost. Over time, we can drip in innovations and to further enhance efficiency, to further reduce cost, but this is not so innovation from my point of view is now not the critical aspect in scaling up.
Thank you, Philipp. Taia, I don't know if you'd like to add to this question.
Yeah, so our dream innovation would really be to have much more efficient electrolyzers, because it's, when you improve efficiency, you immediately reduce the cost of your production. And I also think maybe something else will come very soon. It's the possibility of producing really kind of off-grid, either offshore environment or a big solar park in Australia. And even though everyone thinks this looks really simple, let's put an electrolyzer with a PV panel without no stabilization grid, it's really very, very complex. So those things are the short term that I think we might see and actually come to on the hydrogen production by electrolyzers.
Thank you very much, Taia. Well, I think we've come to the end of our panel. Any parting words for the audience before we go to the next session? So, well, if I may, I'd like to thank all of you for being here today, and for your views on this sector. I think we are at a very exciting time now, and well, I look forward to seeing you either deploying your technology, or and seeing more renewable hydrogen and synthetic fuels out there. I think if you So, well, thank you very much, and thank you to everyone who's been here with us in the audience. Please bear with us, stay here, and next we will have a session on the following session, which is cutting edge R&D for the solar fuels of tomorrow, and we'll have 5 expert speakers who will be presenting here. So thank you very much.
Thank you.
Thank you. Bye.
Bye.
Thank you.
Thank
Bye.
you. You can stay with us in the audience as well if you want. I hope so. So right in the meantime, you know, as the moderator of the session, 𝗦ci is comes on screen. I'll stay here with you, and I'd like to you know, welcome all the other panelists that we are here. So 𝗦ci, how are you today?
I'm fine, thanks. How are you?
Yeah, great. Well, thank you for being here with us today. I'd like to welcome Denise Uner and Dennis Tommy, Luca Turchetti, and Bettina Muster for being with us today at this session, which is the final session of this workshop, which I think has been very interesting. So you know, I won't say anything else really. I'll stay here with you, 𝗦ci, but I'll give the floor to you, so you can just moderate the session. So I'd like to ask my colleagues as well to maybe stop sharing screens, and yeah, over to you, 𝗦ci.
Thank you, Carlos. Well, good morning, everyone, and welcome to this session. As Carlos said, is a cutting-edge R&D for the solar fuels of tomorrow. It's part of the Hydrogen and Beyond webinar, and we have with us today 4 experts: Denise Uner, Dennis Tommy, Bettina Muster, and Luca Turchetti. And I'm sure we will learn a lot of interesting things with you today. But first, I would like to ask you to introduce yourself briefly, so we can get to know you a little bit more. So maybe Denise Uner, would you like to start?
Yes, thank you very much. Thank you for the opportunity. I'm a professor of chemical engineering at the Middle East Technical University in Ankara, Turkey. My research focuses on catalysis and chemical reaction engineering, and renewables is both a profession and a passion for me. So I will give a presentation on the overview of the need for the renewables and need for the conservation of energy. Now I will share my presentation. I hope everything is visible. So the first slide has the picture taken from the walls of an Egyptian pyramid. It shows the Egyptian god 𝗕𝗄𝗄, as we know, a dung beetle, who is responsible of raising the sun. The foremost responsibility of the dung beetle is actually to bury the animal waste into the soil, so that the soil is fertilized and solar energy is used to grow crops, which feeds the people. So this is how I envision solar energy and its utilization and its contribution to our society in general. Now, then I will ask the question, how much energy we do spend and what is the efficiency? I'll take you to a picture which probably all of you have seen quite a number of times. This is data taken from Our World in Data, picturing the growth of the energy consumption since the 1800s, the technology revolution, the First World War, Second World War, and brings us to here. And it is also segmented into energy carrier concepts like traditional biomass, coal, oil, natural gas, and the others. Now, when we look at the scale of the energies, in order to bring it down to a meaningful reference frame, if you take the annual fossil fuel consumption in 2019, this is 136,000 terawatt hours. Conversion into basic energy units makes it a 10 to 20 scale. So a reference frame for comparison is needed. So I will be dramatic about the reference frame, and I will show you the Hiroshima atomic bomb. Its mushroom has risen 16 kilometers after it exploded, and I think it is going to be important when we are analyzing our current present day energy consumption habits. And it's debated, but the most recent publications say that it is 63 terajoules blast yield has been discharged to the environment. Now, when we take the annual fossil fuel consumption and compare it with the atomic bomb blast yield, we see that our consumption is of the equivalent of 15 atomic bombs per minute. So where does this energy go? This energy goes into the environment, into the atmosphere, and we have to really consider how much heat that we are releasing to the environment in addition to the carbon dioxide and the greenhouse gases and their impact on the environment. Now, when we do the simple calculation by taking energy as a state function, we are going to take the initial state system at a temperature T0, and we are going to have an arbitrary E joules of energies available in the form of heat and or work. But as we know from the first and second laws, any energy is going to dissipate as heat. So we are going to take these numbers and convert to heat. And what is going to be the temperature gradient if we take this energy consumption only of the fossil fuels and release it to the atmosphere? We take the energy consumption, take the atmospheric mass, assuming atmosphere as a mixture of nitrogen and oxygen with an average molecular weight of 29 grams per gram mole, with an average heat capacity of ideal gas heat capacity of 7/2R, I calculate a temperature change of 0.17 degrees Celsius per year. So we just take the fossil fuels, we use them as thermal energy source by driving our cars in thermal power plants or in any other form of thermal energy generation, we induce 0.17 degrees Celsius a year. So this number is 10 times greater than the climate change values reported in the open literature. The climate change reports indicate that it is 0.70 degrees Celsius per decade. But remember, my calculation only included a sensible heat change in the atmosphere. It doesn't take into consideration of glacier meltings, which is a latent energy change. So we know that 267 gigaton ice is melting a year. This accounts for 0.8 10 to 20 joules of that 4.9 10 to 20 joules of energy, and warming up of surface waters and increasing evaporation condensation rates can account for the rest. Now, when we just reread the fine lines, it says that which takes account of the inefficiencies in fossil fuel production by converting non-fossil energy inputs required if they had the same conversion losses as fossil fuels. So I just go back and make a really very crude approximation, as you will see from the numbers. Now, the crudest approximation that I can make for a passenger car is that it weighs 1,000 kilograms, while the passenger is about 100 kilograms. So this amounts a 10% efficiency of simply using a car for the transportation needs. On the other hand, when we look at the engine and chemical to mechanical energy conversion efficiencies in a car, we know that the typical numbers are within 10%. So driving a car is at best 1% efficient. So I think before we start discussing solar fuels, we have to think about our habits and how we consume energy and how we use transportation to induce global warming. We have to readjust our habits and our notions, and we really do not address present-day use of fossil fuels and trying to find solutions and replacement for the fossil fuel use of today's 1% efficient technologies. I think we have to address this in addition to what we are addressing in terms of solar fuel production. So now after I set the stage, the next question I'm going to ask is if we can selectively produce conventional fuels from methane, water, and carbon dioxide, of course, by using solar energy. Now, the traditional method for synthetic fuels is conventional methods, is going through syngas-related reactions using Fischer-Tropsch and methanol synthesis and ammonia synthesis, etc. So the bottleneck of the reforming reactions is that they are endothermic, and also there are selectivity issues. Therefore, we need temperatures at the excess of 800 kelvins. So those temperatures are going to bring our system not into a reactor, but a heat exchanger to be designed. And there's no need to optimize a catalyst. We have to optimize heat transfer. So this is a problem that we need to solve, whether we are going to do solar fuels, solar energy utilization or otherwise. And also we must manage coke buildup. Coke may be a very valuable product at the end. We have to really plan for that also. Now, also we have to pay attention to the second law boundaries because when we sequester carbon dioxide for solar fuels, and when we do it with terrestrial thermal energy, we are violating second law for sure. So if we use solar energy to do dry or steam reforming, we are actually storing solar energy in chemical bonds. Furthermore, if we are using even photovoltaics passing through some thermal routes, we are accumulating thermal energy in the atmosphere, and we have to be very, very careful. So now what we have done was using concentrated solar energy, solar thermochemicals to produce syngas by steam reforming. What we used were quartz windowed reactors, preliminary designs that by themselves were rather heavy, and we have used a solar tracking system with 4 mirrors of 70 centimeters in diameter. And my colleagues who are going to talk after me will acknowledge that these are really rather primitive technologies in the concentrated solar energy, but we were able to achieve focal temperatures of about 1200 Kelvin, even with those small systems. Now, if you remember my note on the thermodynamic limitations of the reformers and the high temperatures limiting the reformers to heat exchangers, the 1 centimeter square or 1 centimeter cube focal area that we can achieve with those small mirrors are sufficient for produce substantial amounts of energy. Now, there was a question in the earlier sessions about why concentration solar power can be important. I would like to answer this at this moment before moving further. There are 2 reasons that why concentration solar power is important. One is because it addresses directly the Carnot cycle efficiency, that we are achieving very high temperatures using concentration solar powers, even with those smaller mirrors. And also, concentration solar power can target 100% of the solar spectrum because it is focusing. So after using that system, we have tried solar thermochemical hydrogen production, which I think is a difficult and surmounting task, given the fact that direct hydrogen water splitting requires really very, very high temperatures. But when we go to steam methane reforming, we have achieved methane conversions greater than 90%, of course, within the intermittency of the solar energy available to us. Now, in the next few minutes that is left for my presentation, I would like to just share a dream, if I may, that if we can mimic to produce chemicals from sun, water, and carbon dioxide, if we can do photosynthesis. If we cannot produce glucose as efficient as a plant cell, maybe we can target producing methane. Now again, thermodynamics is the rule that we should just follow. When we look at the carbon dioxide reduction reactions with respect to the kilojoule per free energy change of the kilojoule per mole of hydrocarbon product, we see a large variety and when comparison to water splitting. But then when we scale it down to kilojoules per mole of oxygen produced, we see a very uniform picture. Seeing that uniform picture just lines very well with water splitting. So in other words, when we look at this picture, we see that water splitting is the energetically most demanding reaction. Once we manage that, we manage the rest of the chemistry fairly easily. So the intermittency was a question in the previous session, and this is what the plant cells do. They do intermittent operations. They do things in confinement. They confine reduction and oxidation in different compartments, and they carry out events, one event at a time. And the problem that we have to solve here is the oxygen problem. The plant cell, all right, in the interest of time, I will skip those and go to a reference that I share with you, not ours, but from the literature, you will find a lot of them. The plant cell uses a cluster, the structure of this cluster and the framework of this cluster in the photosynthetic plant cell is a very hot subject in photosynthesis research. This cluster is the water oxidation cluster, and here the removal of oxygen takes place in a sequence at 298 Kelvin. And oxygen has the strongest bond in the molecules, and oxygen release is the most difficult step in the water splitting, also in reforming reactions. So just to give you another example, a solar thermochemical unit switches between 1500 degrees Celsius and 800 degrees Celsius in order to achieve the water splitting or carbon dioxide reduction, while this plant cell carries out this oxygen release at 298 Kelvin. And this is the focus area that we must focus our attention, because once we solve this, we solve all the other energy conversion problems. So now let me just give you very briefly
2 minutes left.
The water cycle and oxidation cycle that the solar thermochemical process uses. For a water cycle, we take a metal oxide, we heat it up to 1500 degrees Celsius in order for this metal oxide to release its oxygen. And then we have to lower the temperature in order for the water to donate its oxygen so that we can produce hydrogen. So the other thing that I would like to show you is the scale of the processes. This is the red mark shows a bus. This is the Fischer-Tropsch synthesis unit that is constructed, the most recent construction in Qatar, while this plant cell just does that chemical conversion in very microscopic level, as you can imagine, and also it does intermittently. Continuous operations are not acceptable in the living organisms. So this pretty much concludes my talk. Thank you very much. Thank you for the opportunity.
Okay, thank you very much, Denise, for this overview. Next up would be Luca Turchetti. So please, if you could give us as well a short introduction of yourself, and whenever you're ready, go ahead.
Sure, Alicia, thank you for having me. Thank you for all the organizers of this workshop. And good morning, good afternoon, or good evening, depending on where you are, to the attendees of this workshop. I am Luca Turchetti. I am a senior research engineer at 𝗫𝗫. 𝗫𝗫 is the Italian National Agency for New Technologies, Energy, and Sustainable Economic Development. And I'm also adjunct professor at the University of Rome La Sapienza. In the last 10 years, I've been working in the field of concentrated solar thermal technologies, and in particular in thermal energy storage systems, and on the use of high temperature solar heat for the production of hydrogen and solar fuels. Which brings me to the topic of my talk today. Am I allowed to show my screen now?
Yes, sure.
Okay, so can you please just confirm that you're seeing my presentation? Great. Okay, so my presentation is focused on some of the activity of research activities that 𝗫𝗫 has been carried out in the last 10 years on solar fuels, and in particular on solar reforming, which is usually somehow a controversial topic when talking about green hydrogen and renewable hydrogen. And I must confess that I usually introduce my presentations with some provocative questions like the one you see in this title, is there still room for steam reforming in the green hydrogen era? And then I try to convince the audience that the answer to this question can actually be yes, if the proper conditions are met. However, I must say that today, the panelists of the previous session and even Denise already should have convinced that indeed this is the case, and there can still be room for steam reforming also in a future decarbonized energy system. Also, the previous sessions were great, introducing the topic of hydrogen and how hydrogen can be a key element in the energy transition, both by being used as energy carrier or as a commodity, a chemical, like it is mostly used today. And for sure, it is such an element in the European strategy towards decarbonization, towards achieving the net zero targets by 2050. And indeed, we have a European strategy focused on hydrogen, and which envisages by 2030 the installation of up to more than 40 gigawatts of renewable hydrogen electrolyzers in Europe. However, again, when we're talking about green hydrogen, the hydrogen in the future, we basically most of the time talk about electrolysis. And this is easy to understand because, as also Denise has shown before, the way we produce hydrogen today is not compatible with a decarbonized and sustainable energy systems, because today we produce hydrogen mostly, if not entirely, out of fossil fuels by basically reforming processes, mostly by reforming on natural gas, which is a set of reactions. The most important one is the combination of methane and steam at high temperature to produce hydrogen and carbon dioxide. And then you see that carbon dioxide comes out of the process as a product, but also since the process is strongly endothermic, carbon dioxide is also produced by burning fossil fuels to provide the process heat, which eventually leads to the production of a huge amount of carbon dioxide, up to 12 kilograms of carbon dioxide per kilograms of hydrogen produced, which clearly makes us understand why this process will have to be, as it is carried out today, will have to be phased out in the future to achieve our climate targets. Also, however, today this is the benchmark benchmark for hydrogen production, and the hydrogen production cost today with this process is below $2 per kilogram and strongly depending on the gas price, as was mentioned before in the previous session. The operating conditions I told you are high temperature, about up to 1000 Celsius degrees and even above in some reactors, and high pressures up to 40 bars, and usually it takes 2 reactors to carry out the whole process. One first reactor operating at high temperature, and 1 or 2 more reactors downstream of the first one operating at lower temperatures to further push hydrogen production. So today, reforming is definitely considered as the bad guy in hydrogen production. And when politicians, policymakers, media, or general public talk about green hydrogen, basically they all think about electrolysis, water electrolysis powered by wind and solar, which is definitely today the most mature approach to green hydrogen production, but definitely not the only possible approach. There is a wide spectrum of processes that can be considered, combining different types of renewable energy sources with renewable feedstocks that can be used to produce green hydrogen. Here you see a rather articulated picture, which is, by the way, not even exhaustive, as especially for biological processes. I didn't include all the possible options, but we can have biological processes, electrochemical processes like electrolysis, of course, photoelectrochemical processes, and thermochemical processes. So we have different types of possibilities. And today I will focus on steam reforming and on thermochemical processes. And I would say that one of the reasons why steam reforming is considered to be necessarily considered as a gray hydrogen production method is that today we have this wrong idea that power can be green while heat is necessarily derived from fossil fuels, then it is not renewable. But as you could also tell by the previous presentations, it can also be produced out of sun, out of renewable energy sources, out of solar energy. And this is the case of CST technologies, concentrating solar thermal technologies. And in particular, I would like to mention the technology, innovative technologies in this field that have been developed by Enea starting in the early 2000s. Which are based on the use of parabolic troughs, linear concentrators, and the use of molten salts, not only as a heat storage medium like this carried out in today's commercial parabolic trough plants, but also as a heat transfer fluid and heat storage medium with a 2-tank direct approach. Enea has been developing this technology, and these activities led to the development of a first 5 electric megawatt plant in Italy in 2010, and a first cogenerative demo plant in Egypt, producing 1 megawatt of electric power and 250 cubic meters per day of desalinated water. What I would like to emphasize here, since the issues related to the intermittency of the solar energy has been correctly highlighted several times before in the discussion in this workshop, is that this technology can rely on an existing commercial and consolidated thermal storage solution that allows to store the solar heat in the existing CSP plants up to 17 hours at full capacity. So here you see a couple of pictures of our facilities in the research center in Rome, Enea's research center in Rome, where we have a full-scale parabolic trough concentrator which we use to test components of the solar field. And here you see pictures of the plant that has been built within the MATS project in Egypt. So you see an overall picture of the plant, the solar field, the innovative thermal energy single tank, the thermal energy storage tank, including an integrated steam generator. So how can we use these technologies, this concentrated solar technology, to bring steam reforming out of the gray hydrogen era. Of course, this simple scheme represents how we are producing today hydrogen by reforming. So we use fossil fuels, we produce carbon dioxide both as in the flue gas and as a product of the reaction. This is rejected into the atmosphere. Solar reforming of fossil fuels could be a first step towards the full decarbonization of this process, just by replacing the heat source with solar energy, with concentrating system. And finally, if we use a renewable carbonaceous feedstock for our reforming, for feeding our reforming process, for example, by producing biogas and then out of biomass and then reforming biogas, we can have the whole process as net neutral, net carbon neutral, or even carbon negative in case we apply some CCS process downstream of the reforming process. There are basically two main approaches. One, which is, let's say, more widely considered, which is carrying out the reforming at the usual high temperatures. And this can be achieved with solar energy by using point focusing technologies, for instance, solar towers, and with two possible approaches, either by placing the reactor directly in the receiver, or better said, by building an integrated receiver reactor in which the concentrated solar light is converted into heat and directly used by the catalyst to carry out the process. Or you can use an heat transfer fluid and then carry out the reaction in a separate reactor, which is not necessarily located close to the reactor, to the receiver of the CST system. This approach has, for sure, some advantages, because basically you can use the same catalyst that you use in the conventional process, and all the balance of plant and other components of the process are well known from the conventional steam reforming process. However, there are some main challenges mostly related to the high temperatures required and mostly to the lack of consolidated thermal energy storage solution at such high temperatures. And this entails today the discontinuous operation of the systems. And also, in case we think about the directly irradiated process option, also challenges related to the design of integrated receiver reactor. Today, I want to talk to you about another approach, which is aimed at lowering the reforming operating temperature in order to couple the steam reforming process with CST technologies that today can benefit from consolidated and commercial thermal energy storage solution. And we see that this is really an important feature. So I'm talking about a project which is now concluded, is the 𝗏𝗏𝗏 project, whose main objective was to lower the operational temperature of steam methane reforming down to 550 Celsius degrees, where the project can be actually fed by concentrated solar thermal technologies and using molten salt as heat transfer fluid and storage medium. Of course, there are several advantages in operating at such lower temperatures: the use of lower grade material, higher process safety, the possibility of use a single reactor instead of multiple reactors to carry out the whole project, because due to the lower temperature, the water gas shift and steam reforming can be carried out in the same reactor. And which is most interesting today for us, the possibility of coupling the reactor with a molten salt coming from a CST installation, which allows us, depending on the feedstock we are using, to produce up to 100% renewable hydrogen, and also, as you will see right away, to facilitate, if you want, a carbon dioxide capture downstream of the process. There are, of course, several drawbacks that the project tried to address. First of all, at such low temperatures, the process would, in a conventional reactor, obtain very low hydrogen yields, not acceptable under an economic point of view. And within the committee project, this has been addressed by developing a membrane reactor that, by removing continuously hydrogen from the reaction environment, allows to push yield beyond the limitations that a conventional reformer suffers at such low temperatures. Also, there are problems in there could be problems in the reaction kinetics, and also stability at such low temperatures. And also I would add the catalyst bed exploitation, because the process is strongly endothermic, and it is usually carried out in tubular reactors heated from the outside, which entails the fact that only the outer layer of the catalyst bed is actually exploited for reaction, because the temperature, there are strong radial temperature gradients that don't allow to carry out the reaction and exploit the catalyst close to the reactor axis. So in order to address all these issues related to the catalyst, within the project we developed active and stable catalysts at lower temperatures, and also a monolithic solid foam catalyst carrier, which allows for improved radial heat transport. Here is a conceptual scheme of the ภิ𝗴𝗄 plant. You see the membrane reformer, which integrates reaction and separation in a process under a process intensification point of view. So we have the two reactors in one, and we also include in this single process unit also the purification, the production of pure hydrogen. And we have thermal storage, which allows us to operate the reactor even when the solar radiation is not available. And of course, the heat from the solar field is also used to preheat the feed to the reactor, and also to produce the steam required in the system. Here you see some pictures illustrating the development of the single components that have been studied investigated within the ภิ𝗴𝗄 project, starting from the catalyst, which, as I told you before, are based on a monolithic structure, a foam structure, and where the catalytic material was deposited in a washcot. Also, the use of selective membrane based on palladium to separate hydrogen from the reaction environment. And finally, all these components were included and implemented in a molten salt heated membrane reforming, having a nominal capacity of 2 normal cubic meter per hour of pure hydrogen, which was actually the production obtained in the experimental campaign was actually higher than that. So here you see some pictures of the integrated reactor before putting the insulation. Some scheme explaining how the reactor is built. It is basically a shell and tube arrangement with a membrane in the inner part, and in the annular part of the tubes we have the catalyst. Other pictures of the reactor and of the test loop in which the reactor was included to test it under an actual molten salt stream. I will just be very quick on the results we obtained. Here you see in this picture that the methane conversion obtained against the time on stream of the reactor. You see what is the conversion you can obtain with a conventional reactor, which was actually placed in the test loop. Here it is the conversion we obtained in the membrane reactor, which is basically under the conditions that we have considered, double than the one that you can obtain with a conventional reactor. Also, other pictures, I just wanted to show you that by playing on the amount of steam in the reaction area, but also in the sweep side of the membrane, you can achieve possibly even 100% conversion of methane. And of course, this is not necessarily convenient because this requires high amounts of steam to be produced, which of course affects the efficiency of the process. And finally, we also carried out an economic assessment in a specific scenario, not yet optimized actually, for 1,500 normal cubic meter per hour of hydrogen. And what I want to show you, either solar only or by some integration with fossil fuels. And we obtained hydrogen production costs that are can still be optimized, and that can be also comparable in some cases with gray hydrogen production. Also, I would like to mention that we are now working on a new configuration of this reactor, a planar configuration that can be possibly more compact and even more going towards a process intensification philosophy. I will skip the conclusion because I think it's the message is clear. I just want to steal some seconds more to tell you that within the hydrogen TCP of the International Energy Agency, we are currently launching a new task focused on renewable hydrogen production, covering all the different processes that I mentioned before, not only reforming, but also water splitting, electrochemical, thermochemical, water splitting for electrochemical. So if you're working in this field, I really encourage you to go to the website of the TCP and check the information about this task in development. And if you want to know more information, please fill in the new expert application form. I will be glad to give you more information and have you on board on this new task. So with that, thank you for your attention. Apologies for the delay. And of course, I will be glad to take any questions later.
Oh, thank you very much, Luca. Very interesting. So next up would be Dennis Thami.
Yes.
Yeah.
Hello,
Okay.
everybody.
Hi. So the same. Yeah, go ahead.
Yes. Yes, my name is Dennis Thami. I'm acting head of department in the Institute of Future Fuels of the German Aerospace Center. And yeah, I have been mainly working in the past on solar thermochemical cycles, especially the sulfur-based ones. And this brings me to my talk today. So I'm still seeing Luca's slides, so I don't know if he has to stop sharing first.
Yeah, so sorry, Luca, if you can stop sharing, you can see the stop sharing button at the top of the screen. There we go. Perfect. Thank you very much. And over to you, Dennis.
Okay.
Whenever you're ready, start sharing. And I'd just like to remind everybody at the audience that you can send in your questions. So I've seen a few, and yeah, we'll have time to go through them after the presentations have been delivered. So over to you, Dennis.
Okay. So then I hope you see my slides.
Yeah, I can see them well.
Very good. Okay, so the topic is baseload power production with solar sulfur. And so I'm focusing in this presentation on the aspect of beyond of this workshop. The content will be, I will briefly introduce our new Institute of Future Fuels. Then talk about sulfur as a solar fuel and a thermochemical storage medium. Introduce the solar sulfur power generation cycle. Then speak about the recently completed European project Pegasus and give some conclusions and an outlook. So the Institute of Future Fuels started operation this year. It has large-scale infrastructure, first of all, in its on a site in Cologne, a solar furnace and a solar simulator. And in Jülich, close to Cologne, we have the largest artificial sun of the world, the so-called Synhelion. It is planned to further extend these facilities in Jülich and, for example, build something like a Jülich solar fuels hub in the future. Research topics are chemical and physical fundamentals, then development of solar chemical processes, demonstration of these processes, and then also the overall assessment. So then let's look at sulfur as a storage medium here. Here you see the mass-based energy density. And you see that sulfur is already coming quite close to gasoline and is definitely much higher than molten salts, which is used in CSP plants nowadays. And the advantage of sulfur becomes even more obvious if you look at the volumetric energy density, where it is even higher than hydrogen. If you compress this hydrogen to 700 bars, which is state of the art today, still sulfur has a much higher density here. And this is an advantage, for example, if you think about transportation on ships. So let's look at sulfur in industrial processes nowadays. So it is the raw material actually for the sulfuric acid production, the world's most produced chemical, with an annual production rate of more than 200 million tons a year. And therefore, sulfuric acid is even an industrial measure for the development of countries, as it is needed for the fertilizer production. Nowadays, the sulfur to make the sulfuric acid comes from fossil sources. So on the one hand side, the desulfurization of hydrocarbons via the Claus process, and from metallurgic processes like ore roasting. And here you see the world production in 2017. It was 80 million tons of sulfur. It is quite cheap with $111 US per ton. And as I said before, most of it comes from the desulfurization of hydrocarbons and also from metallurgic processes. What is another advantage of sulfur, besides its high energy density, is the fact that you can store and transport it very easily. And this is important because, as I said, it's needed for the sulfuric acid production, and it has to be transported all over the world, either in solid or in liquid form. And in solid form, it is a powder or particles. You can transport it on trains, trucks, or in ships. And if you heat it up to about 140 Celsius, it becomes liquid, and it can be even transported in pipelines, rail trucks, or rail cars. So then let's look at the thermochemical cycle to make solar sulfur. The actual goal is here to start off with concentrated solar thermal and produce baseload electricity power, completely independent from the solar input. And how do we introduce the solar energy? We use the well-known process of the decomposition of sulfuric acid, which first of all gives SO2. This is sulfur dioxide is a toxic gas which can only be treated safely on site of a chemical plant. However, if you introduce the disproportionation of SO2 here, then you can come to elemental sulfur, which, as mentioned before, is the raw material for sulfuric acid plants already nowadays. And sulfuric acid plants don't only produce sulfuric acid, they have a lot of excess heat, which they use to produce electricity. Looking at the reactions, so we have the decomposition of sulfuric acid takes place already at temperatures above 800 Celsius. So this is significantly lower than in other thermochemical cycles we know. Then we have this disproportionation here. In fact, we do lose a bit of the energy because this reaction takes place at fairly low temperatures, which cannot be recovered so easily. However, from a technical point of view, this makes sense, as I mentioned earlier. And then comes the conventional combustion of sulfur, which can take place at temperatures significantly above 1000 Celsius. And then you even come to higher temperatures here than you need during the splitting of sulfuric acid, so during the introduction of the solar energy. And how do we want to integrate the solar energy? At DLR, we have in the last years developed the solar particle technology. Here we use conventional bauxite particles from the fracking industry. They are pretty good for solar application, actually. They are similar to sand, if you want so. They have a high absorptivity for solar radiation. And if you heat them on a solar tower, the hot particles can be easily stored in isolated tanks then used in heat exchangers, and then going to a cold storage are immediately available again for the solar plant. And other than molten salt, we do not have the issue of freezing of this heat storage medium. It does not decompose, it's very stable. We have low parasitics here, and also the safety requirements are significantly lower. And the technology at DLR developed in the last years is called CENTRIC, Centrifugal Solar Particle Receiver. It is something like a washing machine, if you want so. So the particles enter from the top, forming a dense film on the inner surface of this rotating cylinder through the centrifugal forces here, and then the concentrated solar radiation enters into the cavity, is absorbed by the particles, and then we can gather the hot particles at the outlet of this receiver, and through the rotation speed we can actually control the mass flow through this receiver. So let's take a look at the overall process. I will not go into complete details here, just show you that, okay, here we have this solar receiver, we have a hot tank and a cold tank for the particles. Then we have here the sulfuric acid decomposition unit, consisting of vaporization of sulfuric acid, which is completed at about 400 Celsius, and then subsequent decomposition of SO3 forming the SO2, which is then further processed in the disproportionation reactor to give elemental sulfur. And then we have here the sulfur burner to gain back the stored energy. And we have this two storage systems, so for sulfur and for sulfuric acid. And then depending on if the sun is shining or not, we are either producing sulfur or we are producing sulfuric acid. And then another feature of this cycle can then be seen here, meaning that you could envision to produce the sulfur in the desert as a good solar site, then transport the sulfur to a non-solar site like Germany or wherever else, and there produce the sulfuric acid and also the base load electricity here. So as you might see, this can be very easily integrated in also already existing sulfuric acid technology. So let's take a look at the state of the art here. So usually we have refineries which produce as a byproduct sulfur. The sulfur is transported to the sulfuric acid plant, which produces acid and electrical power. And now we suggest to introduce the solar particle technology here to decompose or recycle the sulfuric acid, splitting it, then further disproportionate the SO2 to come to the elemental sulfur, so that we would recycle the sulfur throughout the process and would not need here fossil sources anymore. As an additional feature in our project, we suggest to use gas turbines to further increase the efficiency of sulfuric acid plants and burn the sulfur here and drive the gas turbine with the exhaust. So I mentioned already the European project Pegasus, which was recently completed this year. I was coordinating this project as a representative of DLR, and we had partners from Greece, Germany, Poland, Italy, and Israel. And the main results are, first of all, we further developed the centrifugal receiver technology here. There was a 500 kilowatt prototype on our solar tower in Jülich in Germany, where particle temperatures of more than 900 degrees were achieved. And at Pegasus, we developed another slightly smaller prototype in the 300 kilowatt range for the solar simulator Synlight in Jülich. And here we could show that efficiencies in excess of 80% are possible. So this is experimentally proven. Plus, we see a potential of more than 90% in our validated simulations. And also we performed an integrated test in the Synlight We had transport containers to transport the hot particles to a particle heat exchanger and demonstrate that we can heat a fluid here with these particles. And this particle heat exchanger, we also operated in our lab. It was a shell and tube system with a moving particle bed. And we, in the lab, had an electrical heater with 7 kilowatts. We reached particle temperatures of 870 Celsius here. The reactor had an efficiency of about 70% during the experiments, which are still ongoing. And we had a chemical conversion of the sulfuric acid in the mean of 44% and in the maximum of 86%. As a catalyst, we used iron oxide. And our partner KIT from Karlsruhe in Germany, they developed a novel sulfur burner for application in gas turbines at elevated pressures of 15 bars. Just to explain to you, in sulfuric acid plants today, burners are used operating only at ambient pressure. Therefore, the off-gas here can only be used for steam turbines. And here also some techno-economic study that was carried out. So the suggestion here is, for example, to produce the sulfur in Morocco, transport it via ship to Germany, and then use it here for electricity and sulfuric acid production. So these are the 4 steps you can see here. And then the fresh sulfuric acid produced in Germany or other locations can then be used also in chemical processes where it is usually been diluted. And then the spent sulfuric acid can be shipped back to the desert to recycle it. The overall efficiency of this thermochemical process to make sulfur is in a range of 25%. And this is close to other thermochemical cycles, for example, in the hydrogen production we know. And if you look at the electricity produced here, we come to 8.8%. This is a very high value if you compare it to other power-to-X processes, for example. And in an economic study, we could show that at a CO2 price of about 130 euros per ton, this technology would be economically competitive. This brings me to my conclusion. So I showed to you today that sulfur has a high thermochemical energy density. It can be very efficiently transported and stored as solid or liquid. The solar sulfur cycle allows for baseload power production, a complete decoupling of the solar source and the power production. And it has the potential to integrate in already existing sulfuric acid plants. Then I showed to you the results of the European project Pegasus, where particle centrifugal receiver prototypes were constructed and tested on sun and also with simulated sun. We carried out integrated testing with the Centric and the particle heat exchanger. We operated a particle reactor for sulfuric acid splitting, and also partners of us developed a prototype for sulfur combustion suitable for gas turbine application. Furthermore, we did process simulation and techno-economic studies. As an outlook, currently we still have a national project in Germany on the sulfur cycle, where we also analyze the disproportionation as a reaction here. And we are currently planning a follow-up of the Pegasus project in one of the upcoming European Congress. So with this, I would like to thank you for your attention, and I'm glad to answer your questions.
Thank you very much, Dennis. And last but not least, we'll have Bettina. So whenever you're ready, go ahead. You are muted, I think. I can hear you. I can't hear you.
I see what's going on, Bettina. So you're actually sharing your entire screen, and also I can't really hear you. So there we go.
We can still we can't hear you, Bettina.
We can't hear you. Maybe try without the headset. Just unplug it and see if that works. So do all of you, just to give Bettina a little bit of time, I'd like to let you know that we actually are preparing a questionnaire that we'll send to you, just to ask you for feedback on this activity and on the other types of activities we should carry out to to fulfill the objective of this project, which is to accelerate the commercial deployment of solar fuels, solar fuels and chemicals. So we'll send you an email probably tomorrow or the day after regarding this, but yeah, just wanted to give you advance warning. So how are you doing there, Bettina? Everything all right? Unfortunately, still can't hear you. So I don't know. We don't know why. There are right. So there could be one reason. So if you check on your browser, actually, I noticed that your sound was off. So if you go to the top of your browser, you might actually want to check the your settings there at the browser at the top next to your search bar. That's one place where you could check. Then also on at the bottom of the screen, there is a microphone icon, so you can actually check there and choose all of the options you have there for microphone. In the meantime, actually, if you think that's okay, maybe I'd like to invite Dennis and Luca back on screen, and of course Alicia, and we can start going through some of the questions, just to give you a bit of time, Bettina, and see whether you can manage to solve these problems. So you can even switch your camera off if you want, and then try to solve the microphone issues. So right. So well, Denise and Dennis and Alicia, welcome back. So let's go through some of these questions. There are some people obviously asking for the actual levelized cost of energy of all the solutions being shown. I'm fairly sure, so you have been asked directly, Dennis and Luke as well. I'm fairly sure, if I've done enough of these to know that this is not the kind of thing that you share openly, but are there any kind of orders of magnitude that you'd be willing to talk about in terms of like the costs that you may reach, and what is needed to get it to like to commercial deployment?
Yes. Yeah, so there is a reason why I did not give this number in the presentation, because in fact it is misleading in this cycle, because as I mentioned, it does not only produce electricity. The electricity is actually a byproduct of the sulfuric acid production. Although one has to say that the sulfuric acid industry earns a lot of money with the electrical power they make here. So this is in fact of importance. And so one also has to keep in mind that the electricity we make here is really at base load. So you cannot compare it maybe to conventional CSP plants, where you do have some seasonal dependence, and you cannot produce the electricity, for example, outside of a desert area or so. And but our studies do show that even considering all this, the electricity price is still in the range of 15 to 20 cents per kilowatt hour.
Thank you. Thank you very much. And I think one of the other questions was related to the space requirements for these technologies. So, you know, any idea of how much space you would need to produce a certain amount of hydrogen?
Is this question for me?
Yeah.
So actually, we are not making hydrogen, we are making sulfur and electricity. And actually, the space we are requiring is not really making a big issue here, because, as I mentioned, these plants are in the desert. Yeah, so it is an area where you do not really have an issue with limited space or so. And yeah, but I do not have the exact numbers now on my mind. But of course, we did these calculations in our techno-economic studies. So if the audience is interested, I can of course look it up and send it out.
Mm-hmm. Okay. And well, you're receiving lots of praise for your presentation, Dennis, and someone is asking how many hours of sunlight, I think he wants to ask, per year do you have in Jülich?
Do you want to work in Jülich, or why are you asking? Do you want to join our institute?
maybe Fernando.
Yes, we are
Oliveira, he says yes.
Yes.
He says.
Okay. Yeah, then you are invited to go to our website and look for open job offers there. Yes, well, of course. To be honest, I mean, you know, Germany, we do not have so much sun as you have in Italy or Spain or in the desert even. But this is not really a big issue for us, because we are doing research here. And if the sun is shining, we have very, very high quality of the sun. So it is very clear sky. And then we can do our testing and simulate the conditions one by one as we have them in the desert. So. Does it answer your question?
So yeah, he's asking whether the results were obtained in a solar simulator.
Yes, both. So on the one hand side, I was maybe a little bit confusing. So there were actually two prototypes, one on the solar tower in Jülich, where we came to these high temperatures of 900 plus. And then we went back to the solar simulator in a little smaller scale, because we wanted to have to show the high efficiency of this technology also, where you need very high concentration, very perfect situation here of the concentration. And there we could then demonstrate also that high efficiency is possible with this particle receiver.
Thank you. Dennis, and there are also a couple of questions for Luca. I think one of the questions, which is, you know, a question I don't know if, I think I probably mentioned to you that I could foresee at this type of session, and it basically says, you know, if you already have full hydrogen production, if you already have electrolysis and processes that you use then why are you developing these technologies? So maybe, Luca, you could give us, an overview. I know you went into it in your presentation, but an overview of, what's the objective of research and what the advantages are.
Yeah, I think that first of all, our main idea is that in order to fully exploit the versatility of hydrogen as energy vector, we must consider all the production processes, starting from different energy input types, renewable energy input types, and also feedstocks, depending on the local availability of these resources. Otherwise, if we count only on one single technology, I don't think we're really building an actually resilient energy system. So one of the reasons why hydrogen is considered as a key element in the transition and the actual operation on such a decarbonized energy system is exactly for its versatility, the possibility of producing it out of different energy sources. So this is the reason why we are exploring not only water splitting in an area. Of course, I have also colleagues working in electrolysis. I belong to I presented the research carried out by the Solar Thermal Energy Division, which is not only about reforming, we're also working on thermochemical water splitting. But I think reforming can also play an important role as also, let's say, to reach the industry in the short term, because this allows us to not to completely change the current hydrogen production paradigm. We can progressively, in a first step, replace the energy source with a renewable one. So we could carry out steam methane reforming powered with solar energy, and we cut down the CO2 emissions already by doing this. And then, of course, in a fully decarbonized system, we will not be able to do the steam reforming on methane. But we will be able to carry out steam reforming of biogas or other processes based on a renewable carbonaceous feedstock. So this could be the role of in the future, let's say at steady state, in a fully decarbonized system of reforming, which is not to substitute electrolysis, but to complement electrolysis, again, to exploit the local mix of resources available. Okay.
Thank you very much, Luca. I don't know, Bettina, whether your audio is working. Yes, it is.
Solved it. Yes, I'm
Great.
sorry. Yeah, sorry for this incident.
These are things that happen, when you go live. So no worries. We start again, and yeah. So I think we'll stop answering questions. We'll go to Bettina's presentation, and then we'll answer any questions that remain after.
Yes, thank you.
All right. Thank you very much.
I will talk today a little bit about our research on, let's say, more niches on solar wastewater treatment for hydrogen and ammonia production. So this is now, when you compare it maybe with the scales, rather, let's say, research that we are doing so far in smaller scales, and also that would be, let's say, an addition to all the other hydrogen and or renewables initiatives we've learned today about. And this is more about regional and localized production of hydrogen and ammonia based on wastewater treatment. If we go to the next slide, we see a little bit the research group we are working at here at IAE-INTEC. So IAE-INTEC is a non-university research institute in Austria. We work on renewable energy technologies, a lot on energy grids, renewables in many different aspects, also for industry. And in my research group on water and process technologies, we have a strong focus on gathering valuables from waste streams and wastewater. And we mainly work in cooperative projects are embedded in several international expert networks on IEA basis, and I've learned with interest on the upcoming hydrogen task before. Yes, we also integrated in the working party of process intensification. So we try to actually use novel process engineering approaches to really leverage valuables from wastewater in a sustainable way. And we do that, as you see here below, from, on the one hand, even design of components up to lab and pilot testing, but also system integration and sustainability analysis. There are two main aspects that I would like to talk to you today about. The first one, if we go to the next slide, we see is on ammonia separation via membrane distillation. And this could be, and that's why I think it links very well also to solar, this could be easily driven by solar thermal energy because it actually requires very low temperature energy. So it could be waste heat, but it could also be low temperature solar. And the focus here is that we try to, or let's say that we have actually this problem. On the one hand, nitrogen is on the one hand problematic in many waste streams. In many cases, we have a too high nitrogen concentration, too high ammonia concentration to actually deal with that. And we need a lot of energy in wastewater treatment plants to actually get rid of the nitrogen in wastewater. On the other hand, nitrogen, and especially specifically ammonia, can be a very high, let's say, valuable, either as chemical, but of course also as energy vector. Ammonia has very high or very good properties. It's easily stored. It has an even higher energy density than hydrogen. And with that can be seen also as one, let's say, important energy vector of the future. The applications areas where we see this, or where we have a potential here, is of course wastewater treatment plants. We have in biogas plants usually high ammonia concentrations in digestates, in biorefineries, in food industry, etc. So we find across our industries actually quite a lot of nitrogen polluted streams where we could leverage this process on. If we go to the next slide, I show you a little bit, let's say, two different configurations of how we can separate ammonia from wastewater. And actually, we have here two different possibilities. Usually what we do is that we, in membrane distillation, we literally do what it literally says. We distill via a membrane. So in membrane distillation, the driving force is a vapor pressure difference across the membrane. And what we can do in case of ammonia is that we actually have a higher vapor pressure based on the free ammonia that we have on the feed side. And on the permeate side, we bind the ammonia either to an acidic stream, such as ammonium sulfate, or we, based on a very low vacuum, we apply here a certain vapor pressure difference and get ammonia as in gaseous form or as ammonia water on the permeate side. Only free ammonia can pass the membrane, so we need to have, let's say, a feed stream at higher pH, or need to raise that pH. And then, as said, we have these two different options. On the left-hand side, you see the DCMD, direct contact MD. Here we get ammonia water, or let's say with an acid ammonia sulfate, or let's say other products that could be used as fertilizers. And on the right-hand side, you have the vacuum membrane distillation, where ammonia is collected in gaseous form. So this could be directly an energy vector. We have been working, which is shown on the next slide, in projects in both terms. So here, now on the left-hand side, rather the ones which link to as ammonia in the gas form. And one of those that I would like to put up front today a bit is ammonia to power, this project, where on the next slide I show you more in detail the concept. So in the ammonia to power system, the idea was that we use streams like wastewater treatment streams, digestate or urine even, treated with vacuum membrane distillation, gain ammonia in gaseous form, and with that was the aim, to reach even 500 grams per liter ammonium concentration here, and then fuel an SOFC system. The whole concept of this, because coupling really the wastewater problem to a low temperature technology that can generate electricity and high temperature waste heat, we believe here that this is really could be a strong concept for the future. And what you also see on this slide is that we actually won the state prize of research for this just recently. But I would like to further focus on more technical details here. We looked at, when we go to the next slide, please, we looked at different influencing parameters in this work. So how can we actually optimize this vacuum membrane distillation process to get very high concentrated ammonia gas streams? And we did find out a lot of, let's say, influencing parameters. And one, of course, is the ammonia concentration on the feed side, because it adds to this vapor pressure difference and the driving force. Vacuum pressure is, of course, influencing the parameters, but also temperature. And here, interestingly, the lower we actually run the temperature, the better we are on the selectivity. So it means the lower we run the process, and this is also, let's say, for solar thermal, maybe even possible then in countries with not such high radiations, we actually have higher selectivity, so we get more ammonia over the membrane than water. However, still in this vacuum membrane distillation, we always have a trade-off. Yeah, how much ammonia flux do we get through, and on the other hand, how high is actually the concentration of our gaseous product? And if we look at if we go a step further, we also found out here that we can even increase this with new strategies. So we actually found a way of how we can decouple the water and the ammonia flux. We're now in next projects looking also in more functionalized membranes that could even enhance the performance. And it also has to do a lot with really optimizing the temperature of the operation and these operating parameters. And of course, we also have to ask ourselves the question, what are the real SOFC requirements? So far, we are cooperating with AVL here as an industrial player. And so far, there are now tests being done on their SOFC stacks to really find out, is it actually 50% ammonia concentration, or what's the ideal concentration range here? And it is very important in future to look at stable performances. And we've partly proven that already this year, where I would like to show you now a few results, however, in the direct contact mode. So not yet in the VMD mode, but in the direct contact mode. And just to give you an idea of how this can really work, I show you now some direct contact mode results, which we would like to transfer then to the vacuum mode for ammonia gas separation. So in the direct contact mode, it's actually very similar. You see here the point of integration on the right-hand side above the picture. For example, if we look at wastewater treatment plants as one integration scenario, we have an anaerobic digester, we have a centrifuge that separates the sludge from the centric water, and the centric water is usually fed back to the main basin. And of course, in this centered water, there is a lot of nitrogen. So when you fed these back to the main basin, this is also why you actually need to put in a lot of energy in the wastewater treatment plant to have an aerobic denitrification process here. And now if we take this water and try via MD to get the ammonium out, this is really highly beneficial also for the energy consumption of the wastewater treatment plant. And in this case, as I said, we didn't work for the gaseous product, but for ammonium sulfate so far. But as we've just learned here, also the sulfates can be very nicely integrated then in energy cycles. We just learned in the last presentation. And here, if we go to the next slide, I can show you that here in the lab, we could already prove that we can have pure ammonia fluxes if we optimize our operating parameters. So we found a way where we can actually really decouple in this operation mode the vapor pressure difference of water and ammonia fully, and reach here 100% of ammonia selectivity. And the interesting thing for solar, for really solar thermal, low temperature energy is that this process now, as we run it, runs at 38 degrees temperature. So this is really nothing in terms of in the difference of other temperatures. Of course, the problem is also it's a membrane. How does it foul? How stable is the performance? And here on the next slide, I can show you or assure you that we did now already work in a pilot plant over the past year with 14 square meter membrane area. And we could show that we, let's say now we have this module installed in July, and up to now, we don't see any performance degradation. We can actually remove 99% of ammonia. We cover 95% of the ammonia on the permit side, so there are a few losses over the system. We have a very low ammonia concentration in the effluent, so this is also interesting if in case of this water should later then go to the even to back as let's say freshwater use, and we can work really stable. And I think this is very important, specifically for such a membrane process, because we even stopped in between. We had shutdowns because of a pre-filtration problem, but not of the membrane itself. And the system, as I said, so far never showed any performance deterioration. If we now would apply similar things and this is what we aim at in the next year, to really work in these new operation modes also for the vacuum membrane distillation. We already predicted some, let's say, some business cases, and these are summarized on in the next slides. So if we would now say, okay, well, we take this concept as we have it now for the direct contact, and we now transfer the optimization parameters we found out last year to the ammonia fuel generation, we strongly believe that we could really reach this 50% ammonia in our gaseous product stream. And then we did some, let's say, some calculations on when would such system pay off. And of course, if we have to say, let's say, be obvious about the fact that in wastewater treatment plants, we do have a lot of ammonia, but again, this is not something that's then available in megawatt scale. Yeah, so these are rather maybe 10 to 50, maybe 100 kilowatts SOFC systems. So it's really more for the localized production and to, let's say, help really on these local waste treatment problems. And what we can see here is that we have, let's say, with estimative costs on how this could develop, payback periods of 5 to 7 years, also depending, of course, on lifetime of the systems. But however, here in this scenario, we were thinking, or let's presuming, because of these very low temperatures that we need, that thermal energy is freely available. So this is also now important for let's say, the solar side. I think such processes, if we go for low temperature solar thermal, this solar thermal energy actually really would almost have to be available for free in order to make such systems economic. However, we also know that the ammonia prices and let's say other cost scenarios change now dramatically. Let's say even fertilizer costs, I think, tripled over the past years. So this then again can make these economic calculations more beneficial. Yeah, and my last minutes I would like to spend on a second topic that we are also working at our research group, and this is also embedded in IEA Task 62. In IEA Task 62, we actually work on, in the solar heating and cooling program, we work on solar-driven wastewater treatment. And one of these aspects on solar-driven wastewater treatment is also new photocatalytic or photoelectrochemical hydrogen production. Here, as I show on the next slide, the core expert is 𝗷𝗶𝗄𝗍 from CEMAT, and they are already working also on this combination of photocatalytic wastewater treatment and combined hydrogen production. And we have here, on the next slide, we have here, let's say, a new similar approach in a national project where we work on solar photoelectrochemical wastewater treatment. And the point here is that we actually can combine the wastewater treatment, so the oxidation of pollutants, with the production of hydrogen in solar photoelectrochemical processes. In the next slides, I show you a few details. So let's say the idea of coupling wastewater treatment with hydrogen production is not absolutely new. There are several studies around. The wastewater components act as electron donors and can actually increase the efficiency. And there are, let's say, available studies that talk about solar to hydrogen ratios of 5 to 15% that can be reached via this coupling. Yeah, and our approach in the project that we will just now start at the Institute, if you go to the next slide, please, is that, yes, I'm coming to my end, is that we actually here work on multi-component wastewater. So on the one hand, we will be working on wastewaters from vegetable production, where we have pesticides in. We will be working with pharmaceutical wastewaters, with wastewaters from the pulp and paper industry, and there especially with the focus on EDTA removal. And with these multi-component wastewaters, really try to make a novel PEC system to produce hydrogen. And our target is really to reach higher than 25% of solar to hydrogen ratio. And how do we want to realize this? Here, our expertise is less the catalyst. This is linked to the partners. But our expertise is here to really bring in a novel process engineering approach. So to really develop a best concentrated system, and via a new rheology in the absorber tube, enable here very high mixing of viscous streams. Then we can have a better light penetration and enhanced, let's say, path of the light to the catalyst, shorter reaction times because we have an intensified mass and energy transfer, and we will, because we can decouple actually particle velocity from the net flow velocity, be able to tune the, let's say, net flow velocity according also to solar light. And this is something, that will allow us to control the reaction residence time based on the available light. And we have the pre-studies done with such a reactor design, not for photoelectrochemical processes, but for other processes with very promising results on mass and energy intensification. And yes, we are now looking forward to extend this to solar photoelectrochemical hydrogen production via wastewater treatment. Yes, I think with this is my last slide. And with this, I already come to the end. So there's a small insight into our work, very much linked to wastewater treatment, and yeah, more, let's say, maybe in different scales than some of the other contributions we learned so today. But I think important niches and specifically, sustainable because of this combination of, let's say, a waste problem and renewable fuel production. Thanks a lot.
Thank you very much, Bettina. So now I think, I don't know if we have time for more questions, Carlos, I think so.
Yeah, I think we can answer a couple of questions. So, I'd like to invite our panelists back on screen, please, and then we'll answer a couple of questions and then we'll close the webinar. So I'll let you choose a question, Alicia.
Let's see. Well, I have actually, I think you all mentioned it, but just to summarize or to sum up, like the advantages of producing the renewable fuels with your methods instead of the traditional ones. I think you all mentioned a little bit of it, but just to, let's say, just summarize a little bit better. Who would like to start?
Yes, I can repeat once again. So, I mean, the solar fuel we are looking at in my presentation was sulfur. So compared to the state of the art, sulfur is nowadays completely produced from fossil fuels. So therefore here we would produce a very green product comparatively. And another advantage of sulfur is that it is really a seasonal storage. It can be transported easily all over the world, stored easily, and therefore is available for power production also in non-solar sites.
Thank you. Maybe Luca?
Alicia, sorry, but I had a problem with my audio. Could you please repeat the question?
Sure.
And can you confirm you can hear me?
Yes, yes, I can.
Because yes.
Just a general question, like to summarize a little bit, the advantages of the method you presented compared to traditional ones.
Well, of course, if by traditional we mean conventional reforming, by the advantages I think are clear. We're talking about the benchmark here is a type of processes that we will not be able to use in the future if we really want to meet these targets that we have set. So definitely this will be necessary to phase out those processes and move to sustainable ones like the one we have presented. If we're talking about other renewable hydrogen production processes, I think that in the future green hydrogen will be mostly produced by electrolysis, but there will be room for other type of processes like the one that I presented to complement electrolysis in meeting the growing hydrogen demand that we can expect in the next year, and then at full and at a steady state, let's say, in a fully decarbonized energy system.
Thank you. Bettina?
Yes, I think I highlighted it in the end of my presentation. I think for us, it's really this coupling of a waste problem and an energy vector generation. So I think and it is specifically important because these waste problems, they're sometimes not solved yet. So for example, in the solar photoelectrochemical hydrogen production and the coupling of pollutants, we are looking at pollutants that are not easily degraded. So we are even starting now a process on microplastics in this way, because here then it's really on the one hand a problem, but on the other hand we can make an opportunity out of it. And this is the same with ammonia, right? So ammonia, if we can here really have localized production of ammonia as energy vector and then use it where it's required and really produce electricity, let's say, out of your wastewater. I think this is this is just an important addition to the large-scale green fuel generation that is initiatives that are going on.
Thank you. I see here a question. I think it's for you, 𝗦ci. The extraction of sulfuric has a huge negative environmental impact. So, what is the alternative behind the typical extraction?
Yeah, so I must admit I did not understand the question completely. I could maybe just say what I understand from this question. So probably it refers to the desulfurization of hydrocarbons, which is done nowadays. So oil and gas, which is as a fossil fuel available, has sulfur in it, and the sulfur has to be extracted before you burn the oil or the gas, because this sulfur burns to SO2, and you do not want to have SO2 in your exhaust. And then the sulfur is, as I showed, further used for the sulfuric acid industry. Of course, in the future, at a certain point, we will not have fossil fuels anymore. So we will not have oil and gas, and then we will not have this resource of sulfur anymore in these from these hydrocarbons. And therefore, we will have to think about recycling of sulfur in our industry. So maybe to stress this point, sulfuric acid is extremely important for the world because it is needed for fertilizer production. We cannot go without, and we have to think about a recycling of sulfuric acid. And therefore, we have to think about a way to get solar energy into this process. And this is what I was actually suggesting here, and which we were investigating in our project.
Thank you. This question is for Luca. So can you please provide some information on the cogeneration demo plant in Egypt? Are the results promising?
Yeah, I've just seen that question. Actually, I didn't see the questions in the chat box. So yes, the results are promising. What I have to point out is that the plant I mentioned is actually a research infrastructure. It's a very small scale plant. We're talking about 1 megawatt electric, which is very small for a CSP plant. And of course, this entails challenges in terms of costs. And however, there are publications already out about this plant and the performance. I will point Fernando Oliveira to those publications, and because this way the data that can be published are, as soon as they are available and publishable, are reported in such publications. So the results are encouraging. Of course, we're talking about a very small plant, so it's not a commercial plant. This probably, I didn't point it out quite clearly before. And these data, therefore, don't refer to the actual operational commercial plant. It's not operated 24/7. It is operated for limited periods for experimental campaigns at the moment. And of course, now that the consortium, which involves both European partners and Egyptian partners, is looking for other frameworks to fund the continuation of these tests.
Okay, thank you. And I see there's another one for you that says, what's the efficiency of the high temperature solar reforming? Yeah,
that's always a tough question to answer, because with the word efficiency, we refer to many different things, especially if we include a solar collection, a solar energy collection step. So what I can tell you that for the high temperature, so not the type of reforming we've been considering in the research I presented, but other groups worldwide have been considering, if you refer to the efficiency of thermal efficiency of the reforming process itself, at peak conditions, you may refer to the usual efficiency of reforming processes, which ranges from, let's say, 60 to 75%, depending on how you're able to optimize your system. But you have to, if you're talking about solar to fuel efficiency, you must include, and then you have to clearly define what is your denominator in the efficiency, which is not always simple. In the CSP community usually refers to the direct normal irradiance collected on the mirror surface. In this case, you may consider a 50% reduction, roughly. Dennis, who is working in point focusing systems and tower system, may be more precise than me. Reduction of the, let's say, loss of the DNI available on the solar mirror at the receiver. And then you have to also consider for the further reduction due to the reforming process.
Okay, thank you. And I think the rest of the questions that are in the chat were already answered, or you're answering them.
Yeah, I think.
Can I just a bit? If there is time, there is one last question that I can see. I would like to reply.
Please,
if we're not too late.
Yes.
Yeah, because I have seen that there is some positive criticism by Thomas there that basically is not convinced about the idea behind the solar reforming research. What I would like to point out is, first of all, this is not, I mean, solar reforming, the reforming of biogas and in general renewable carbonaceous feedstock is not only an ENEA idea, but it's envisaged in the strategic research and innovation agenda of the Clean Hydrogen for Europe PPP of the European Commission, and also in other research agendas. Thomas says that resilience comes from having a dispatchable supply and storage, and he doesn't see this in 𝗫's research. What I would like to point out that the 𝗫's research was exactly focused on this, lowering the temperature of steam reforming in order to be able to couple the process in order to be able to couple the process with CST technologies that today allow for long-term storage. Long-term means over a night. We're talking about 15 or to 17 hours in existing CSP facilities at the rated full capacity. So I agree that definitely resilience comes also from the dispatchability, and definitely this is why we also focus on CSP and CST technologies to power hydrogen production processes, because CST today is one of the few dispatchable renewable energy technologies. So sorry for taking this more minute to address this.
No, that's okay. So you know, I think that's what we're here for, right? To you know, debate and answer questions. I think as with all good things, you know, this workshop is coming to an end as well. So Alice, I don't know if you have any further comments or.
I just wanted to thank you all for being here, all the speakers we had today with us. I think you showed different approaches for, say, a same problem, right? And I think it's very exciting to see that there are so many possibilities. And yeah, thank you also the organizers for making this possible, and the viewers, the audience that have been with us today. From our side, that is all. Thank you, Matt.
Thank you very much.
Thank you very much.
I think, you know, before we go, I'd just like to say to thank all of you for being here and everybody at the audience, and to say that, you know, that I think the main takeaway I get from this session is that there is more than one way to get solar fuels and chemicals, and you know, for some of them, yeah, we have a very well-known processes, but for others, you know, it's worth actually researching. So we think, you know, diversifying is a good way to go when it comes to these resources that we'll definitely need in the future. And this is what we try to do in the Solar Fuel Now initiative. Look at all the different pathways we have for generating solar fuels, and not just hydrogen, because I think hydrogen is the one that is you know, is fashionable now for very good reasons, but there are many other chemicals that need to be produced in a renewable manner, and yeah, so we'll look at how those can be produced using solar energy as well. So once again, you know, thank you very much, Bettina, Denise, Alicia, and Luca for being with us today. And thank you to everyone who participated in the workshop as well as an attendee. We'll actually send you a questionnaire tomorrow or the day after to ask you for specific feedback. So on future activities we'll organize. So thank you very much, and see you here next time.
Thank you.
Thank you. Bye-bye.
Thank you. Bye-bye.